In this marathon, we will start from the very basics, installing NGSPICE and GNU-PLOT, and move step by step into writing, simulating, and analyzing real circuits. From understanding SPICE netlist to libraries to mastering troubleshooting, parameter tuning, test vector creation, waveform handling, and advanced analysis like noise and distortion. We will cover all of them. So, whether you are a beginner or budding engineer in VLSI design, stay tuned. Every section will build your skill and confidence to handle real-world circuit simulations. So, let's get started and stay tuned till the end of the episode.
Hey guys, welcome back, and we are installing NGSPICE today. Here you can see NGSPICE website. This is the website. Here you can see NGSPICE is an open source SPICE simulator, and all the menus here you can explore by yourself. The page that you should go is the documentation, because the installation I will show you hands-on, that will do not need to search here. And today we are installing this in the Linux environment, so that is not documented here. In the documentation, you can find the different manuals here. The NGSPICE manuals, you can go through it to understand it. And here you can see there is a tutorial. If I mark it, you can see this is the tutorial links. Now let me click onto the tutorials. Here, there are several tutorials. NGSPICE tutorial for beginners, control language, manual, ICAD, or eSchema GUI. Okay, so all these things are there. So there is an electrothermal simulation, device model. So this is the menu of the tutorial, which you want to explore. Now if you scroll down, right, there are several tutorials on the web. So you can see this is the tutorial on the web. So all these things are there. You can explore them by yourself. And here are some video tutorials. You can see here the video tutorials are clubbed and listed as per category, and here by the presenter. And you can see different NGSPICE tutorials videos are there. You can go through it. So here we will stop, and let me go back to its home page. The things I have made crisp. What you need, you can just go up to that point and search things. Another thing I would like to mention here, you can see here, this is the GNU-PLOT. So this is the website. Don't worry, I will provide the two website URL in the video description so that you can find them and you can use them to directly go to the page. You can see here, so the GNU-PLOT is a portable command line graphing utility. So you can see here, this is a 3D graph and this is a 2D graph. So this kind of graphs, if you want to plot inside the Linux environment, you must need the GNU-PLOT. So here are several other things. You can go to the documentation page here. Here you will find, right, the documentations. You can see the PDF format is here, right? Current is here, old is here, and the older is here. So from here you can also download the documentation. And let me go back, and here is the download page. But however, since we are installing in Ubuntu Linux, I'll show you the direct way of installing from the command prompt. Now let me go back to here and we open the terminal. Here is our terminal. The command that I will type here first to install the NGSPICE. So you can see I have typed sudo apt-get install NGSPICE. So this is the necessary and sufficient command. However, in case in your machine, if you need some dependencies, you have to install it separately. You can go to stackoverflow.com to search how you can install the dependencies. So let me hit the enter key. It is asking for the password. Let me give it. And you can see the installation process has begun. Right, it is proceeding, and you can see the installation is done. So after this, just point out things here. So you can see 0 upgraded, 1 newly installed. This 1 newly installed is NGSPICE, and you can see that lot of packages. You can see a message here, right? Sudo apt remove all these packages. So this is not related to the NGSPICE. However, these are some packages. They are lying in the background in the Ubuntu, the installation that I currently have. These are not needed, or you can say as these packages have become redundant. That's why the installer, the sudo apt installer, right, that is messaging us to give the sudo apt auto remove to remove all these redundant packages. So this is don't have a headache whether it is related to the NGSPICE or not. So these are some packages that are lying in the Ubuntu which is now redundant. You can remove. This is a separate message, so don't relate it with the NGSPICE. So let me clear the screen. Here now we will install the GNU-PLOT. So let me type the command. So I have typed sudo apt-get install GNU-PLOT. So this is the command to install in the Ubuntu Linux, and this is sufficient here right now. In your machine, in case you need some dependency, during the installation you will be prompted and all those dependencies have to be installed separately. And how to install those dependency, you can go to the stackoverflow.com and there you will get some suggestions. So let me proceed here. Let me hit the enter key. You can see the installation process has begun for the GNU-PLOT. So here you can see again the removal message is coming. So you can see this is coming again and again. So this is related with the system. So that's why it is giving. And here you can see one is newly installed, right? So this one is GNU-PLOT, which sudo apt-get install command has installed. So here we are done with our installation. Let me close this terminal here. And let me go back to the folder. Here I have kept one SPICE file. Let me open it with the text editor. So you can see here this is a plain and simple RC circuit. We have a C1 and R1, right? We have provided VDD and we are providing a AC here, AC signal here. And if you go down right, here is a OP. OP is for the operating points. Those things are here and you can see the dot control. In a detailed tutorial, we will go for all this description of this SPICE thing. However, this is an installation episode, so we will keep it short here. And here you can see the run instructions. So this entire thing, right, is dot control and NC. This is for this. This is for your NGSPICE instructions. This is your SPICE circuit and this is the NGSPICE instructions. So here you can see it is calling the GNU-PLOT by itself during its run, and it is plotting the different voltages. And here I have kept or commented some writing raw files. I'll not go in this direction today. However, just I'll show you how you can run this thing with the NGSPICE and how GNU-PLOT opens up all those plots that are here. Let me close it. Let me open a terminal here so that we are directly inside the folder where this is. Let me do a ls. You can see the rc.sp is here. Here you can go for the rc.sp. So you'll run the SPICE file with NGSPICE. So let me type. And next to the NGSPICE command, we will give the rc.sp, the SPICE file that I have just shown you. And if I hit enter, let us see what happens. So you can see here, different plots are coming here. 3 GNU-PLOT windows have opened. Let me minimize this. And here you can see. Here you can see the NGSPICE has run. This is the past part of its log, run log. And here you can see this is the topmost comment, that is the first line of the SPICE file that has been echoed in the screen, and you can see all these things are coming because of the control commands that we have given at the last. Here you can see it has run, and let me go back here, the plots. So this is one particular plot and here is another plot. 3 plots are there. So there are 3 plots here. This is of your example purpose. I am not going into the circuit or what is inside the graph or how to interpret the graph. I am not going in that direction because this is an installation episode. You just have to become familiar how to install and run that tool. Don't worry, I will provide this particular circuit file, the SP file, in the video description, from where you can actually download it directly and you can use it after the installation. You can see this is the first graph, this is the second graph, and this is the third graph that has been generated by the command. Let me go back once here. Let me open it with the text editor. So here you can see in this dot control section, that means it is the beginning and the NC is the end. So here I have kept 3 GNU-PLOT command and this is generating 3 different graphs. And here you can see the 3 different graphs are here. So I think here we'll stop in today's episode. So today we have installed the NGSPICE and the GNU-PLOT in the Ubuntu operating system, and I have also shown you the documentation and the tutorials pages from where you can pick up your learning or start your learning. And I also have shown the running of the NGSPICE and which automatically calls the GNU-PLOT, and that's how our episode ends here.
Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the structure of a SPICE netlist. Next, we will talk about a typical SPICE netlist and its various sections. So, when you are writing a SPICE deck, that is the SPICE input file, there will be several sections. So, you will get familiarized with the different sections that generally a SPICE deck or SPICE input file has. Next, we will go for the detailed description of a CMOS circuit. First, we will describe, then we will go through the SPICE deck. Next, we will go to the code and its output of that particular CMOS circuit, which we have described in the previous point. So this will be sequentially described and then the circuit will be shown and its output will be shown to you. However, in other cases, we will not go in such detailed description. Instead, we will directly go to the code and the output. So the first one is the RC circuit, where we will describe the code and show the output in RC circuit. Next, we will go for the SPICE code and output of a RLC circuit. Now, once we have gone through this PPT, next section we will move into our terminal and we will simulate all these 3 circuits using the NGSPICE and we will display the waveform using the GNU-PLOT. So, there will be a hands-on, and in the video description, you will get all the links to download this 1, 2 and 3. These 3 SPICE netlists you can download at your end and you can run them with the help of NGSPICE and visualize the output using the GNU-PLOT. So here we will close our today's episode after doing all these things. So here we are done in the menu. Let us move on to the next slide. Structure of a SPICE netlist. Here, with the help of the infographics, we will put a small imagery in your mind that what are the sections present generally in a SPICE netlist. So, the first one is title. So, there will be a text title and this will be a commented one. Generally, this is the first line of any of the SPICE file that has the title. That means a short description of what circuit it is. Next, we have controls. So this could be at the beginning of the SPICE deck or it could be at the end. It depends from one simulator to another simulator. For NGSPICE, we will have these controls at the end of the SPICE deck. As we go through the examples, you can see for other simulators, these controls may be somewhere else. Next, there are sources. That means we have DC and AC voltage sources which we apply on the components will be available in the section of sources. Generally, the sources are defined first and then we start the components because the type of the sources, whether it is AC, DC or mixture of AC and DC, so those have to be determined first and what voltage and etc. Those will be there. Next, there will be models, SPICE models that comes from the BSIM compact modeling, and all those models are supplied by the foundry. So you don't have to code, you have to just include the available models. For the practice of a student, some models are inbuilt to the simulator so that you can pick up those models and directly use them. Additional models have to be included separately, which are provided by the foundry. So those models will be captured in the model section. Without the model, you cannot run any SPICE simulations. This is a bare essential thing because any SPICE component has to show its behavior electrically, and for that we need the SPICE model. In the Verilog A series, and you can refer to the Verilog A marathon, I have talked about the models. The link of that particular episode is given in the description. If you are curious about the models, the compact models, and what is the present day scenario of all these models are described in a nutshell in the Verilog A series in the first episode and at the very beginning. So you can go there and use the chapters to learn about these models. Link is given in the description. The next section will be containing the components. So there will will be two set of components. One is the active components and another is the set of passive components. Generally active components which can amplify or rectify these. That means your semiconductor components, and passive components like resistor, capacitor, inductor, which do not have a property of rectifying or amplifying. So all those components will be there, and there could be mixture of both active and passive components in the component section. So it will be the circuit, basically the description of the circuit with the interconnections among the components. The next section is the subcircuit. Now, some of the components may not be sufficient to operate with the models. In those cases, subcircuit will be there. Subcircuit is a compact version of the component and the model for a particular block, and that block has some individuality as its input and output. So, those subcircuits will be used. In industry, this kind of subcircuit may come from the foundry, or it can be internal to the IP team. The IP team may give you the subcircuit and you can directly use it, or it may come along with your foundry PDK. So what is PDK and all? We already have a video on that. In case you want to know and you are very much curious about the PDK and its components, you can watch the episode. The link is given in the description. So here we are done with this particular slide. So we have 6 different sections. First one is title, next one is controls, next one is sources, then we have very important model, then we have components, and we have special subcircuits. So all these things will be there inside a particular SPICE deck. So this is the infographics that can help you to have an idea, but to become proficient in SPICE deck writing, right, you have to go through multiple examples and you have to try out your own circuit that is drawn on pen and paper, convert it in the SPICE netlist and run it with, here we are using NGSPICE and GNU-PLOT, so you can use that, and this way you can become proficient in coding of the SPICE netlist or writing of the SPICE netlist. We are done here. Let us move on to the next slide. A typical SPICE netlist. So here we will go through the different parts of a SPICE netlist line by line. First, we will have a flow chart where we'll show that what are the parts, and then we'll have an example. So side by side, I will map those things. First, there will be title as we have learned in the previous slide. Next, there will be model and simulator options. The very next zone will contain the supply and sources, that is the voltages that has to be provided for a circuit run. The next section will contain the components, that means the circuit detailing, that means what are there, both the active and the passive components as necessary. Next section will have analysis and plotting. This section in NGSPICE will have the control option, right? So you will see that, not for the analysis, but rather for the plot one. And finally, we will have an end statement. End statement ends the SPICE deck. That means anything you write after this end will not be considered for the SPICE simulation. So now you have the different sections of a particular SPICE deck. So let me display a SPICE deck for your knowledge. Here is a SPICE deck. This first line is a comment and this is the title. You can see this is the title. So title is only one line. So here you can write one circuit's description, what type of circuit it is, and you may write if there is some PVT values to it, you can write it. So those things will be kept intact for the person who do not know about the circuit and will get knowledgeable by seeing that particular line. So it is a very brief information about the circuits and its behavior, etc. The next part is the model simulator options. Here you can see there is a statement called include models.lib. So this comes as the include statement. This is .lib, but you can understand this is not the .lib from the STA. This is the .lib for the SPICE models. Generally, this may come from the foundry or it may come from the IP design team. Whatever is applicable in your case, you will get it. Then you will have some options. So here in generic manner, I have write 4x, 4y, 4z and 4k. So these will be some words and so this will define the operation of the SPICE simulation. So these options. Don't worry, in this series we will go in every detail of each of these statements. So don't worry. In case we want to include some models will be there. So this particular section here, you can see it is completed using this type of commands, and generally it is at the top after the title. The next section is supply and sources. Now let us see what are the voltage supply. We have a comment here. The comment character is star, that is the asterisk that makes a line comment. So in case you want to comment a line which you are not using, you can use the star also, even anywhere in the SPICE deck. So here you can see there is a pulse train. So we will go in detail of all of these sources. Here I will not go in minute details, rather I will describe here what is there. So here we have a source where we have voltage value and we have pulse train here, you can see, right? And then we have a AC value, right, where we have a sign, and these are nodes. So data 0, these are nodes of the circuit. So the nodes could be alphanumeric, either they could be numbers or they could be the small words. And here another one is the exponential. Various kinds of voltage supply, that means one particular supply will be the basic DC level. Generally a circuit needs a DC part to get turned on, and on top of that there could be a pulse train, a sine wave, a exponential wave, anything like that, that actually determines the operation zone of that particular circuit. All those additional sources will be applied. So there will be a DC, and in addition there will be a different kind of waves form of the supply. It could be pulse train, it could be sine wave, it could be exponential, anything, or it could be a periodic one that is written with the PWL. So all those things will come later. So we can conclude that this section corresponds to the supply and sources. Supply means the basic voltages that will help the circuit to turn on, and the sources means it will act as a stimulant for that particular circuit. The next section is the circuit components. Here you can see we have the circuit components, and here we can see that up to this part, and here we can close it. So here we have the particular component L. Generally we have the type of the component by its initials, right? L is the inductance, C is the capacitance, R is the resistance. It could be also alphanumeric. Okay, we will go in this nomenclature details later episodes so that you will have the proper knowledge about all these things. Then there will be nodes. There are two nodes, and then there is the value. So here, so no value is written. So there are some default values to it, and we will also discuss in later episodes. So here we will not go in that much detail. You can see the circuit components here corresponds to the component section. So this also has a comment which we have created with the asterisk. So now the next section is the analysis and plot. So here we have transient analysis, TRAN. We will go through the detail of all of these transient AC and DC analysis types in later episodes. You have to stay tuned for that. And you can see there is a plot command here. This plots. But however, for the GNU-PLOT to get activated, we have separate plot commands, and that is what I am saying, because these things may vary from one particular simulator to another particular simulator, because this plotting involves a separate GUI window to come up with the plotting of the data which has been achieved by the SPICE simulation. So here you can see there is a print. It will print the data in the console. That means the terminal that you are using to run the SPICE deck. That means the SPICE input file or the SPICE netlist. And here you can see there is a end statement. So anything after this will not be considered the part of this particular SPICE netlist. So if you write any components after this, they will be discarded. So end means here our SPICE netlist is ending. So this is the very simple example of a SPICE netlist, and we have segregated the different sections, that is title, model and simulator options, supply and sources, components, analysis and plot, and finally the end statement. So any circuit will follow this pattern. In addition, there could be some plus minus things that will vary either from design to design or from one simulator to another simulator. That you will get educated once you start the SPICE netlist coding, or you enter into the VLSI industry. There you see any particular SPICE netlist, you will see some additional things. Now, one thing I would like to say here, from one EDA vendor to another EDA vendor, there could be some changes inside this particular SPICE deck. They will be somehow similar. In addition, there could be some differences maybe in some of the area. Okay, so while you are defining, there could be some of the commands that could be different from one vendor to another vendor. You have to be careful about that, because there are several EDA vendors and all of them provide SPICE tools for the simulation. As in the previous episode, we have talked about the pure SPICE, accelerated SPICE, and the fast SPICE. These three could be from three different vendors. they might have some intrinsic difference of having the SPICE netlist. So you will get familiar, don't worry, you can consult the manual and there you will get some examples and all, or the tool installation folder may have a examples folder. From there you can get educated. That is not a cumbersome thing for you. Here I am touch basing the facts so that you are not get lost once you enter the VLSI industry. We are done here. So let's move on to the next slide. The SPICE description, the CMOS circuit. So in the upcoming slide, we will show you a PMOS circuit. Since CMOS is the kind of unit block of the VLSI chip, right? So here we are giving a short description what you will see in that particular SPICE deck. We'll go in a very speedy manner so that you can reach to the SPICE deck in the next slide and you can correlate. So here goes our SPICE details. First one is the voltage sources, right? Next will be the voltage sources. Here is the VDD, supply of 5 volt. Next, Vin, the input voltage of a pulse train of amplitude 1 volt. So you will get all of these things in the upcoming CMOS circuit. Next, we have transistors. M1 is the NMOS transistor with source connected to the ground, gate connected to the input, that is in, and the drain connected to the output, that is out. Basically, this is a CMOS inverter circuit. So in is the input of the inverter and out is the output of the inverter. The NMOS transistor has a length L of 0.5 micrometers and width of 1 mic. You can vary or change them as you wish in the SPICE deck and see what are the result of those changes. Next is the M2. M2 is the PMOS transistor with source connected to the supply and the gate connected to the input, that is in, and the drain is connected to the output out. The PMOS transistor has a length L of 0.5 micrometers and the width of 2 micrometer. So here you can see it is 1 and it is 2. There is a reason why generally the PMOS has a larger area. You can find that fact in your textbook. Why this? I can give you a hint. It's related to the pole mobility and the speed of that particular carrier. So can you do that? Can you find the answer why the PMOS has a double size or larger size from the NMOS? Next, we have the load capacitance that acts as a load for the output. So we have a C1, load capacitance of 1 femtofarad connected between the output and the ground. So this will act as a load because generally the PMOS circuit will fade into some output, and here we are considering a capacitor as our output, and that is called the load because that takes the input from the output of the CMOS circuit. Next, we have the analysis. We have a transient analysis of 0.1 nanoseconds to 10 nanoseconds. So we have a transient analysis there. So this is the quick description of the SPICE netlist of a CMOS circuit. In the next slide, we will go through that particular SPICE netlist and you have a quick impression of all these things in your mind. So now let's move on to the next slide. So here we have our CMOS circuit. This is our CMOS circuit, and you can see there are several sections which you have learned from the title up to the end statement is also present here. You can relate by yourself, but let me point it out for you. So here the title is this one, the CMOS inverter circuit. The next we have the two model statements which goes to this particular section. That means the models and simulator options. And here you can see the NMOS PMOS levels are there. That means these are the BSIM levels which I have talked about earlier, which you can learn about from the Verilog Marathon. Link is given in the description. So here you can see as we cross this model section, then we have the supply and sources. So here we have the supply and sources. So this is the supply. This is the basic DC supply that will energize the circuit. And this is the source. That means it will act as an input stimulant to that particular source so that we can have a corresponding output and we can compare whether our circuit design is correct. So this is the section of the supply and sources. In the next section, we have components. So here you can see three components are there. First one is M1, that is the NMOS. Next one is the M2, that is the PMOS. And we have a output capacitance P1, that is the load capacitance. So these are the components. So these two are active component, and here is the passive capacitance which do not have the capability of amplifying or rectifying a signal. So here you can see the total components. Three components are there. We are done with the component section. Next, let us go to the analysis and plot. So plot will be later on. Here we have the analysis. analysis, right? The transient analysis. The transient analysis start from 0.1 nano and it goes to 100 nanosecond. So our analysis part is here. Now let us look into the next section, which is very unique to the NGSPICE and GNU-PLOT combo. I have emphasized this point that this control part will be different from one simulator to another simulator. So the control part for this NGSPICE starts with a control statement and ends with the NC, that means the end control. So in between anything could be there, that will be for the control part. So OP will be the operating point analysis, then run, the simulation will run, and then it will call the GNU-PLOT with a temporary file GP. GP will contain the data. GP will have some extensions. This is the prefix, and there will be some extensions of the files. Once we run this, you will see that instead of GP you can write something else, and then the GNU-PLOT will plot the V out. Out means this particular node. Let me see this out node, and V in, that is the input node. Where is this one? So these two node voltages will be plotted in the GNU-PLOT in the same window, and here our control ends. So the control block, rather than this is plot block, so this is the plot one. The plot one is here. You can see analysis was there, it is earlier. So analysis and plot section is done. Next we have the end statement. Here is the end, right? End will end the SPICE deck, and once we run this using the NGSPICE and the GNU-PLOT, we'll have this kind of output. So there will be a V in, which is a pulse, right? And again we have a V out, which is again the pulse, but they are in inverted form because they are going through a inverter which inverts the voltages. That means it will convert one level to the zero level. That means it will convert 5 volt to 0 and 0 to 5 volt. So you can see here the waveforms of different colors. So V in and V out, you will see in greater detail once we run this by hand at the end of this slide. So you will see there. And this is the kind of output of the GNU-PLOT, which has been triggered from inside of the NGSPICE. So this will be fed to the NGSPICE, and automatically the GNU-PLOT will be called by this command, and this output will come. So you see that we're done with this particular example. Let us move on to the next example. Here we have the SPICE code of a RC circuit. Now let me display the code, and let me segregate the different sections. So this is the title which goes for this particular title part. Now we don't have model sections, but we have some simulator options. That is the PARAM is here, right? So this belongs to this, the second one, the simulator options. Okay. And we have supply and sources. So here we have supply and sources section. So that is the VDD, and we have a AC voltage here, and we have commented this. Since this circuit is a passive circuit, RNC, it do not need to get energized with a DC voltage. Okay, the previous circuit was active component, and that needed some voltages to be applied to them to get activated, but this do not require that. So we can directly go to the sources. Here is the source, that is the input source, which will provide the input variation so that we can get a output variation. Okay, next we have the component section. Here it is very short, R and C in series, right? So we have C and R here as components, and you can see this param res is defining the resistance value. So you can change here and it will get automatically passed on to this particular resistance value. The component section is done. Next is the analysis and plot. The analysis is here. It is the AC analysis. So AC has its nature of defining. So it is a decade. We will go in the detail of this kind of analysis later on some other episodes. There will go detail how the AC is defined and what are the different components of a AC or transient or DC. So you have to wait for that. Here we will not go in that much detail. The next one is the plot or the control part. Here the control starts with the dot control command and ends with the NC. So here is the OP again, as similar to previous SPICE deck, and we have run similar to previous SPICE deck. Again we are calling GNU-PLOT. We have a temporary file GP. This is the prefix, and we'll have some extensions to store the data that can be used to display the data in the GUI window. And here this particular node, the output node, the voltage will be shown in the output as a plot. And here at the end of the netlist, we have the end statement that ends the SPICE deck. So we have all of the things here. Here you can see that the things are a bit jumbled up inside the SPICE netlist. That means all these sections are not in sequence. So you have to face these things in an industry, and you have to get prepared that all the sections will not be in the sequence. But however, all of these sections will be present either directly in this particular file, or there will be a .include statement, and you will have another file which is pointed by this include statement, and that file will contain all the details. You have to mentally prepare for that situation. So once this code is run, that means once this SPICE file is run through the NGSPICE and the GNU-PLOT, this kind of waveform is generated. And you can see this is a logarithmic scale here, this way. And here we can see the output is swinging like that. This is the AC analysis. This is the RC circuit, right? So you can see it is a low pass filter kind of thing. And as the frequency goes over to a particular frequency, it is attenuated. So this is a kind of low pass filter circuit. We are done here. So let's move on to the next slide. SPICE code and output of a RLC circuit. Without any further words, let us have the circuit. So here again we have the SPICE circuit. Again we will have all these sections. Let me map these sections for you. The first one is the title. Next, we do not have models because these are passive components and we don't have any simulator options here. So this particular section is not present here in this particular day. So this is another option that you can face. Next we have the supply and sources. So here you can see we have a AC voltage here, the AC sine waveform that acts as an input. This is here. So this is the supply and sources section. Next, we have the component section. So component here you can see R, L and C. This is a RLC circuit. So this particular components are passive components and they do not need a DC voltage to get energized. So the DC voltage source is missing here. Here the component section is done. Next we have the analysis and plot. So analysis, we have transient analysis. So we are giving it, and for printing, right, we have the print statement here. One mistake is here that this particular end has come. This should not be here, as the end statement will come at the end, and here we have the end, right? So this is one mistake here. Now next one is the plot section. The plot section is the control section, starts with the control and ends with the NC. So here we have OP, run and GNU-PLOT command similar to the previous SPICE deck. And here we have voltages 1, V1, V2 and V3 for displaying. And at the end, you can see here the end statement ends the SPICE deck. So once we run this circuit with the NGSPICE and the GNU-PLOT, we get this kind of a output. Okay. So there are some of the voltages are overlapped. You can see the sine wave is going through, right? This is a kind of transient response of a RLC circuit. You can do any changes here as you like, and you can run it again to get the different kind of outputs, and you can store the whole output as snapshots to compare them. Okay. Or another thing you can do, that you can change the GP to something else so that the database for the GNU-PLOT changes. Here we are done with the 3 examples. And now we will move on to our terminal to run this particular SPICE decks by NGSPICE and the GNU-PLOT combo. So let us go to the terminal. Welcome back. We are in the terminal here. Let me do a ls here. So we have 3 different circuits that we have just shown in our slides. So let me open each SPICE file. We are using gvim and the alias is here G. So don't get confused. You can use your own text editor to open this. So let me open the CMOS circuit. You can see we have this particular CMOS circuit along with the control statements for the GNU-PLOT, as we have seen in the slide. You can download this SPICE deck from the link given in the description. So go ahead, download it, and you can run as I am going to show. So let me close it and let me use NGSPICE. So before using NGSPICE, let me check where it is installed. So I will type which NGSPICE. It is there in the user bin NGSPICE. So in this path, the NGSPICE is there and it will run from there. And next, let me check for the GNU-PLOT. So here it is GNU-PLOT. We have a separate episode where I have shown the installation of NGSPICE and GNU-PLOT together. The link of that episode is given in the description of this video. In case you do not have these 2 things installed in your system, go ahead, see that episode, install these 2 binaries in your Ubuntu Linux, and then you proceed for trying out the 2 examples. Let me proceed as we have the 2 different binaries installed in the system. So let me run the SPICE deck. I will type NGSPICE. followed by CMOS, and I'll hit tab. The deck name automatically comes as we are using the TCSH. And you want to learn about the TCSH, we have an entire marathon on Linux. The link is also given in the description. You are not familiar with the Linux, so please go ahead and learn the Linux because it is very essential in VLSI. Now let me hit the enter and you will see the magic. So let me show you what has been gone through in the terminal. So once we have run the SPICE deck using the NGSPICE, the NGSPICE has first turned on and it says no compatibility mode selected. It is unimportant right now to us, but it could be in case some netlist compatibility thing you have to incorporate. In that particular case, it will be important, and we are skipping this at this moment because we are going through the very initial stage of running the SPICE netlist. Now, if I go down further, you will see that the circuit is a CMOS inverter circuit. This comes from the title, and here it has run. All the steps have been printed in detail. What the values are there, the transient time started at 0, then the temperature is this, T-norm is this. All these details are there. These are not needed until you face any error. If you face an error, you need to look at this particular log. Some of the SPICE tools generate a .log file containing this informations. So once this is done, NGSPICE terminal has opened here. You can see, although it has executed the control commands as we have given, and here is the GNU-PLOT. Let me expand it. So you can see here that V in is in green color and V out is in purple color. So you can see the input as it goes like this, right? The corresponding output goes like this. So it is acting as an inverter, and this is true for all these sections. So you can see all these sections are behaving very similar fashion. So the inverter is performing as it is expected. So we are done with this particular GNU-PLOT. I'll close this window. To store this, you have to take a snapshot. Now we are done. Let me put an exit here from the NGSPICE terminal and let me do a ls again. You can see there are some files, gp.data and gp.plt is there. I think the plt corresponds to the plot. You can rename it, or you can give a separate name gp. Instead of gp, you can give a separate name in each of these decks and you can save all this data. Okay, that is up to you. For me, I'll remove these two files and I'll go for the next SPICE netlist. So let me do the cleaning. Now let me open the rc.sp, that is the RC circuit. Here it is opened and you can see it is very same as you have seen in the slide, and even this commented part is also same. You can download this, the link is given in the description. From there you can download it and run it as is. And here is the control part for the simulator NGSPICE to invoke the GNU-PLOT. So let me run it. We have NGSPICE, then rc.sp. But before that, we have to clean the GP files. Let me do a rm gp then star. I am removing all the GP files here. So now again, let me do the NGSPICE and do rc.sp. And once we hit this enter key, you will see the magic and it's there. Again, you can see here in the terminal, right? You can see here all the details are logged here from the SPICE run, right? Which is necessary only when you have a problem and you need to look where the problem is coming from. That time you need to go back and see this particular log. And now the output is there. Let me maximize this and you can see here that it is acting as a low pass filter. That means up to some frequency right here, it is passing everything, and after that it is attenuating the output. So we are done here analyzing the output. So let me close it. Let me put a exit. We exit from the NGSPICE terminal and let me remove the GP files. I have removed them and let me clean the terminal, and here let me do a ls. So remaining is rlc.sp. Let me invoke using the NGSPICE. Before that, let me open and show you that this is the same file that we have demonstrated in the slide. So you can see here, these are the components, then it is the sine wave voltage, then it is there, and it's same because we have a end statement. Even the mistake is there. You can see the end. Let me remove this line by inserting a asterisk here. So the end will be at the end of this SPICE deck. Everything remains same. Let me close it and let me run it. Let me type NGSPICE followed by RLC, and once I hit enter, it will do the magic. So you can see here the NGSPICE has run, and here is the log. You don't need this log until you face any error. So here you can see what has been gone through. Okay. Now let me go directly to the output. Here let me maximize it. Here you can see there are three outputs, V1, V2 and V3. Some of them are overlapped, so we can see only two of them because any two of them is overlap. So can you find which one of these two are overlap when you run the SPICE deck? You do that and let me know in the comment. Three waveforms are there in this particular LCR circuit, and we get a output like this. So we are done here in the GNU-PLOT. So let me close it. And let me exit from the terminal. We are done. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the SPICE simulator types, that is the difference of look and feel. There are several types of SPICE simulator and we will differentiate them in terms of look and feel. Next, we will point you out to the episode which has the NGSPICE installation instruction demo and the necessary links. Next, we will talk about the internal flowchart or the process flow of the SPICE simulator. This is a generic one and this could be applied to any of the educational as well as the industrial SPICE tools. However, there will be some additional steps in case of a industrial SPICE tool that is specific to a particular EDA vendor, and hence we will not be able to give you the minute details of such industrial SPICE tool substeps. Next, we will dive into the SPICE fundamentals and we will start with the element notation and unit. Next, we will go further deeper on the SPICE fundamentals for the element and symbols. Next, we will go further down in the SPICE fundamentals and we will talk about element notation and unit. Finally, we will dive into the SPICE deck details by sharing the basic informations of the title and the end comments by the title and end, as well as talking about the comments. Now, that's the menu for today. So without any further delay, let's begin. SPICE simulator types, look and feel. Based on the usage of the SPICE tool, there are two broad categories of the SPICE simulator. Basically, these are the two different user perspective or user usage perspective, else there is a division. So the first one is the netlist based, where we have to write a particular SPICE netlist in text form and simulate it using the particular binary. Like we have used NGSPICE in first couple of episodes of this series as examples as I have shown. The next category is the schematic based, and here the candidate is LTSPICE, which is a free tool. We are not covering the LTSPICE in this series. We are covering rather the netlist based SPICE tool in this series because that is the very much fundamental thing. Even you are using a schematic based SPICE tool, under the hood, it actually is simulating a netlist that is generated by this particular schematic tool. The schematic tool at the bottom even uses a binary to simulate the SPICE deck that it builds from the schematic. So in this series, we are going for extreme fundamentals of the netlist based SPICE tool because this is where you start learning in your undergraduate college level, and this is extended for the various electrical characterization in the VLSI domain, as I have explained in the first episode. And the schematic based drawing is for the analog designers who design the analog circuit from the schematic, and this could be a IP level development, it could be a block level development, or maybe for a data design. So that's the basic division or the categorization of the two different SPICE tool available in either in the open and free software or in the VLSI commercial EDA tools. So both have the same kind of divisions. That means the netlist based SPICE tool and the schematic based SPICE tool. We are done with this particular slide. So let's move on to the next slide. Since in this series we will be extensively using the NGSPICE, as I have demonstrated in the last episode with few examples, the installation episode of NGSPICE we already have published even before releasing this series as a episode, and here you can see the thumbnail of that particular episode. You can find the direct link of this episode in the description of this particular video. There is nothing more to say on this, so let's move on to the next slide. SPICE simulation internal flow. Now we are talking about the netlist based SPICE tool internal flow. Here, once you provide the netlist to the simulator, it parses it, and what happens inside the SPICE tool. The reason behind keeping this slide is that once you find a fault or error or something unusual, you have to go back to the different internal steps and check from where this particular unexpected thing, whether it is an error or unexpected result, it is getting generated. The first step is to read the SPICE deck and the .include file. So inc.inc is the shorter form of the .include that is used to include many files like models or libraries in the SPICE deck. So in this way our flowchart will go up to down this direction only. So we'll proceed in this manner for the left hand side of this arrow as well as in the right hand side of this arrow. Next is the init numerical engines. There are several numerical methods that you have learned in your undergraduate level like bisection, Newton-Raphson, all these things. In this particular SPICE simulator or any of the SPICE simulator which is a netlist based, there exist all these numerical methods and they are intelligently picked for case-to-case basis, or even there could be a switch or a option to select a numerical method explicitly by the user. So this could be there, and this is for the initial solution, that is the initial condition solution that is needed in a SPICE deck. We will go in detail of this init and all these things in the fundamental episodes in the upcoming episodes of this particular series. So wait for that, we will go in detail. Now let us go to the next step, that is the not set or IC initial OP guess. So there are two different kind of initialization. One is not set, another is .ic, and there could be some files associated these two also. So once we go in detail of these things, you will see and know about these details. This is because here we are giving the bird's eye view of the flowchart and we are not going details of each and every step because we have episodes later in this series to cover all these things in detail. The next one is the DC bias convergence that happens inside a simulator, and this convergence is based from the numerical engines which is picked by the simulator or it may be specified by the end user. The next one is the AC, DC or transient analysis. So that happens inside the SPICE simulator. These are the basic three type of SPICE analysis that is being used on a particular circuit under test, the circuit that you design in the SPICE deck. Next one is the calculation of @node and @time, frequency and param steps. So all these things are there. Next is the data matrix mining. So what is data matrix mining? So there will be, let me draw a diagram here. You will understand better with the diagram. So there are several nodes in the circuits, right? This is a node, this is a node, this is a node. So these are the nodes where the different components are interconnected. So there are several nodes like this. So all these have to be solved in a matrix method, and that data has to get mined in some data structure which is defined internally to the SPICE binary. So in this step, the data mining will happen and the dynamic calculation, that means the calculation with respect to the time, will be done by the SPICE simulator, the numerical methods inside it, and so on. Next step is the waveform DB creation. Once the simulation has started, right, the data mining has started, the visual output, that is the data, whatever goes to the output nodes of the circuit, will be stored as the waveform database. Now, waveform database is nothing but a database which contains the voltages, currents, etc. with respect to the time. That means the time in the x-axis. So this is a xy axis. So in this axis there will be time. In this axis there will be current and voltages. So all those things will be stored in the waveform DB. And from one simulator to another simulator, this waveform DB is different. For Verilog, there is a file called BCD file. We have already covered that in the Verilog series. And that is a similar kind of waveform DB in the digital simulation. And in analog simulation, there will be .db file, or maybe some DB name will be there, or it may be .raw file. From there, you have to pick up the data. In case of NGSPICE, we have a very easy option to plug in the GNU-PLOT and directly throw the output into the GNU-PLOT GUI, where it shows the current voltage characteristics with respect to time as graphical plots. Multiple windows are plotted as per the instruction. We have already shown this in the last episode. There are 3 circuits we have shown, the different graphs we have shown, already it is there. So for NGSPICE, you don't have to find the DB, but also we have mentioned there is a temporary DB file for the GNU-PLOT. I have pointed out last episode where I have shown the hands-on demo of the 3 SPICE circuits. The waveform DB is created. Next, we have the text output log file. So this is a log file where all these steps, when they are getting performed, all the details of those steps are logged into. That means they have been written in detail. So in case our end user is facing some issue, or there is some question, there is some query, you can go to the log file and you can read it and reach up to the particular point where there is your necessary information which you are looking for. The next step is the .measure execution. Once this waveform DB is already completed, right, there will be a .measure execution that will happen internally. Although this is not that you will completely see this is finished and this has been executing after that, not like that, but internally somehow it manages to perform the different electrical characterization on the waveforms of the SPICE circuit output. And .measure command, these are given to characterize electrically the different current, voltage, and extracting different data from these IV characteristics. Okay. Next is the alter statement, and it's a special statement that helps to repeat different block of codes with a minor change in it. So you don't have to write 10 SPICE deck, instead you write 1 SPICE deck, and there you repeat a particular block where there is a small change, and for that different set of results will be generated. That is the alter statement. We have this in NGSPICE. And next step at the end is stop. So once all these things have performed, right, all these steps one by one have been performed, the simulator stops and exits from the simulation. So folks, these are the basic internal steps of SPICE flow. So there could be some small additional steps in the commercial or the industrial SPICE tools. Obviously, you will have these kind of extra knowledges from their respective manual. That means the commercial SPICE tool will have a manual and you have to look into the manual. So where there is a difference, because this is what is a basic common structure, this will be there. In addition, there could be something that a commercial SPICE tool might have. Those informations are available in the latest manual of that particular SPICE tool. So we are done here. So let us move on to the next slide. So in this slide, we are not showing anything. It's just an interconnecting slide, and this is kept to make you understand that now from this particular slide or the next slide onwards, we will be deep diving into the SPICE fundamentals. And in the next couple of episodes, we will swim through the deep fundamentals of SPICE. That means those are beyond necessary in SPICE. You have to know them in detailed manner. So without any further delay, let's dive. Element notation and unit. Now this is a table, right? And there are 1, 2, and 3 examples are there. So let me point out first element symbol. Here you can see RLC. You can see this is the RLC. Now you can see L, P, and R. These belongs to the inductance, capacitance, and resistance. And there is a number, right? Generally, this is a number. There are 10 inductors. So there will be L1, L2, L3, and it will be up to L10. So like that, it is named. Now there is node 1 and node 2 because this L, C, and R have only 2 nodes or 2 legs in the physical component. So they will be connected to different nodes. I said already, right? here some components are interconnected, here some components are interconnected. So like this, there will be a nodal analysis in the SPICE internally. So for that, we have to define the nodes, and this is the first node, this is the second node, right? This is 1, this is 2, node 1 and node 2. And here you can see the set of node 1 and set of node 2. In case of MOSFET, there will be drain, source, gate, and body. So there will be 4 nodes for a MOSFET. So there you will have 4 nodes here, 1, 2, 3, 4. And hence to accommodate, we have node N. That means it could be more than 2 nodes. It could be 3 nodes like transistor, the PN junction transistor or the bipolar transistor, right? There will be emitter, collector, and base. There will be 3. So after the first 2, there could be 1, there could be 2. So n number of nodes could be there. So hence we keep this node n. Now let us look at the value and the suffix which is kept here, and here you can see A dot B. The unit will be Henry. So L is Henry, C will be Farad, R will be ohms, and so on. So we will come to this all details in the upcoming slide. So I will not exhaust my energy here in this slide. So let us carry forward our energy to the next slide. Element and symbol. Here we will talk about the details of the elements and symbol. As I said, BJT, right? Bipolar junction transistor. Q is written there. So this is a convention, and in SPICE, you cannot randomly write anything for any component. So you have to follow this nomenclature. JFET will be J, MOSFET will be M, gallium arsenide MESFET will be B, diode will be D, resistor will be R, capacitor C, inductor L, and transformer is K. So these are the initials. The next continuation is like this. There are 4 control sources, right? They will have this symbol. So VCVS will have E, VCCS will have G, CCCS will have F, and CCVS will have H. The current source will be I, the voltage source will be V, and the control switches will be W, and the transmission line will be T. So this is like when we are writing a SPICE deck, there will be some lines that begin with, say, voltage source or the current source. So it will be I, say IDC we write, or I10 or I5, something like that we write, and for voltage we write similarly like VDC, VDD, all these things we'll write. These are used as the first character of the line. So these are the first characters of any line that you write in a SPICE netlist for the components. So we are done here. Let's move on to the next slide. Element notation and unit. The first is the A part, and then there will be the B part. So here 10 to the power minus 15 is written as femto, capital F. Minus 12 in the power of 10 will be denoted as pico. This is nano. This is micro. And there is a word mil. Okay, don't confuse this with the milli. Milli is coming in the next one. In the SPICE deck, if you see, there is a unit mil. That is not the milli. That is not milli. Milli is something else. So mil is this and milli is this. So you have to remember this. And as we proceed in the plus powers, so 10 to the power 3 is kilo, 10 to the power 6 is mega, 10 to the power 9 is giga, 10 to the power 12 is tera. Sometimes the giga is pronounced as giga also. So some countries they call it giga, and some countries it calls giga. Both are okay. The next one is the B part, that is the A dot B, which we have seen in the previous slide. And here the units are volt is B, ampere is A, hertz is HZ, ohm is ohm, Henry is H, farad is S, degree is dec, and second is S. So these are the units. So it will be like femtofarad, FS. So there will be millivolt, MV. There will be nano ampere. So that will be NA. Okay. And there will be kilo ohms. So that will be the total unit. That means the A part and the B part will make the unit complete of any component. We are done here. Let's move on to the next slide. Now in this slide, we will talk about the title and end as well as the comments. And this we will do in this slide as well as in the next slide. So let us start. The title line must be the first line in the input file. It contains are printed verbatim in the stdout log file. So this line starts with the star, right? And whatever after star is printed as is in the log file or as well as in the screen, that means the output terminal. So it could be done using the dot title statement also. Comments are like the star, and after anything star is taken as comment in the SPICE deck. The asterisk is in the beginning of the line indicates that is a comment. That means if you have to comment out any particular, say, analysis or component, you have to just put a star in front of the entire line, and that will be commented and that will not be considered in the SPICE simulation. That means the asterisk makes a line inactive to the simulator. End of line comment, or you can say it as an inline comment. End of line or inline comment is like that, couple of commands or components like, and then we have a dollar, and then we have written something in words. So anything like in this fashion, this part will be treated as inline comment or end of line comment, whatever you say. Both are used terminologies in world of VLSI. The dot end line must always be at the last of the input file. So this is the marker that tells the simulator now you have reached the finish line of your running. So you are running for so long, and now I give you the flag to stop. So this is a finish line marker for the SPICE simulator. General form dot global and then node name. There could be some global things that may be used in a circuit, and those are defined by the globals. We are done with this particular slide. Let's move on to the next slide, where we will continue with some of the examples of the things that we have spoken here. Let's move on to the next slide. So here are the examples. First, the title. You can see that dot title, and then we write test of the tile line. Whatever written here comes as the first line of the terminal output or the log file of the SPICE tool. Next, example of a comment. Here you can see star, then RF equal to 1K gain should be used for 100. So this is a comment, and this is the instruction to the designer. Next, check open loop gain and phase margin. Okay, so all these things have to be checked, right? Examples of inline comment is like that. RF2 equal to 1K, then dollar gain should be 100. So this part of this particular SPICE line is comment. Basically anything that is beginning with dollar in between a line is comment. So this part is commented out. Up to this will be read by the SPICE simulator. Let me clean it and say it again. So this part is processed by the SPICE simulator, while this part is excluded from the SPICE simulation. So this is treated as inline comment or end of line comment. Here you can see C1 is 10p, check the open loop gain and phase margin. So this is a comment or instruction for the designer. And here this part will be processed by the SPICE simulator, and this part will be excluded by the SPICE simulator. Examples of the dot statement is simple, the dot end. There is nothing more. After dot end, there is nothing. So it is ending. We don't have anything after dot end. And we have the example of dot global. Dot global means we make some node global like GND or VCC. This is a global node, and anywhere they will be pointing to the same particular node, because say ground is the common ground of the circuit. So we have a big circuit. We have smaller blocks inside that. Everyone will be connected to the basic ground. So the basic ground is the same. So here ground is global, and VCC, the basic power supply that is coming, right, that will be even common to all of the block, that is global. So we make these two things global. Anywhere we write GND or VCC, they will be treated as global. So these things are very common thing in a SPICE deck, and we have started to jump into the basics and fundamentals of SPICE, and in upcoming episode we will continue this deep diving, which is a very basic thing to know, because without that you will be unable to troubleshoot any design that is written in SPICE. In industry, either you go for the IP characterization side or you go for the analog design and characterization side, you will face definitely SPICE netlist. The netlist could be in this particular form or maybe simulator specific form, but anyhow you will face them. So for that we have to know all the details of the SPICE fundamentals. We have started from this particular episode, and we will continue this saga in the upcoming episodes. So we are done here. Let's move on to the next slide. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the SPICE.lead and .include statement and use. So we go in thorough detail of these two. Next, we will explain the subcircuit concepts with the help of infographics. Next, we will explain the model statement, that is the .model statement, with the help of the infographics. Next, we will go in detail of the .model statement and its example. Next, we will talk about multiple model types such as active and passive elements and multiple more model types. Next, we will talk about subcircuit concept with infographics and example. One thing had to be explained that this is a conceptual infographics and this is a command related infographics and example. Next, we will talk about the SPICE.lib structure. So this .lib is very different from the .lib that you have learned in the static timing analysis series. Although both are called .lib, in general, these are library files. The syntax of these two are different. And we will have a simple example of the SPICE.lib, the hierarchical use of the .lib, so that you can understand it well and you can differentiate once you see this .lib side by side with the .lib from the static timing analysis. Don't worry, link of that episode from the static timing analysis is given in the description. Next, we will talk about the SPICE.lib and del.lib features. So there is a del.lib concept so that you will get familiarized in this particular slide. So this is the menu for today. Without any further delay, let's begin. Today, we will mostly talk about the input controls. That means whatever input goes to the SPICE deck, that is the input from the text files or the library files or the parameters, etc. Whatever we have, we will cover in today's episode. Why I have kept this slide? Just to educate you that these are the input controls of a SPICE deck that you are going to face in the VLSI industry. So these are the input controls and the categorization is named as input controls. So I have placed this slide. So without any further delay, let's move on to the next slide. The .lib and .inc statement and its use. Frequently, portions of the circuit description will be reused in several input files, particularly with a common model and subcircuit. So this is basically the code reuse concept. That means whatever code we have in SPICE, whether it is a library or whether it is a model, we are going to reuse it several times. That means we are keeping a file in a particular hard disk location and we are going to point to that file so that that file can be included and elaborated during the simulation. .include serve this purpose. So .include can include any kind of file that may contain, say, parasitics or DSPF. Okay, so that may be used by the .include. Okay, because if you are running a post layout SPICE simulation, there you have to include the DSPF file. We have talked about the DSPF and the SPF in the parasitic extraction episode of the static timing analysis. Please refer to that particular episode. Link is given in the description. So here are the file symbols. That means we are using a James clip here to include several files with the main file. Similarly, we use the include statement, which acts like this particular James clip to include several files into the main SPICE file. And the purpose is depicted here, the reading the SPICE deck and .include files. Let us see an example. Here we use the .include, then we give the absolute path of a particular file. So here we have a path, the user, then SPICE, then common, then bsim3 param.mod. So this is a model file and this is bsim3. Bsim I have talked about in the Verilog A series in the first episode. You can refer to the Verilog A marathon and use chapters to go directly to this particular bsim related information. The link is given in the description. Please watch out that episode if you are interested to know about the bsim models. Now, the SPICE uses the bsim model for MOSFETs and many other active devices. Obviously, all these things have to be characterized and that has been detailed in the first episode of the Verilog A and you can refer to that episode by the given link below. So this has two parts. First is the .include the statement itself and the second part is the absolute path of the file that we are going to include. The .lib statement allows including library descriptions into the file. So library descriptions means there will be lot of data which has been electrically characterized and not by the simulation. These are physically characterized data using the various laboratory tools. And all these data are fed into a characterization program and from there all these model parameters have been extracted. So that is called the library description. So description of all these parameters. And there will be multiple things. At later slide, we have a .lib structure, how these are there. You will understand by seeing that particular slide. Inside the .lib file, a library lib name will be selected. So this is also exemplified there. You will come to know, just know here that there are several sections in that particular lib file which can be called upon by the .lib statement. The statements of each library inside the .lib are enclosed in .lib, libname and .endl statements. So .lib begins a part and that part is ended by endl. Let me clean it and let me point it out. So lib and endl, the .lib and the .endl operates like a opening and a closing parenthesis for a particular block of SPICE code inside the library, and that particular section will have a name, libname. Now this is the syntax, that is the .lib, then file name, then libname. Example is, so here we write .lib, then we give the full path of the .lib, and then we have the name, that is a MOS1. So this is libname, this is the file name. File name means this is actually the file path in your Unix, and this way the thing actually operates inside the SPICE deck. So we are done talking about the .lib and the .include files. So first we have explained the .include, which can include any files, and .lib can only include the library, that is with the extension .lib. However, .mod, if you have to include, you have to use the include. So this is the difference between the .include and the .lib, and the working principle of the .lib and the .include have been explained here. We are done. Let's move on to the next slide. Subcircuit concept infographics. This is a flat part, and here we will explain the subcircuit concept. Now you will ask why we have a subcircuit when we can have a lib. So that concept is explained here, and how that is different from the lib you will come to know. So first we have a typical circuit like this, and you can see there are several blocks. This is a block, 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 and this is the 4 block. So this is a typical circuit. Say this is a VLSI circuit, and this is the design block 1. So that means we are talking about this particular block. This is design block 2. This is design block 3. This is design block 4. So the analog team has developed these 4 blocks separately, and each will have a subcircuit. That means the components, that means the active components, the passive components, all the things are written in this particular subcircuit definition. And one subcircuit definition is different from the another subcircuit definition. In this way, subcircuit 1, 2, 3 and 4 are 4 different subcircuits that has been separately designed by the analog design team, and they are plugged into the entire VLSI chip, as you can see. Now, these subcircuits carry valuable information of each of the block, their characteristics, their details, their models, etc., etc., multiple things. These are different from models because models are for individual components like BJT, like MOSFET, but for design block, you will have a subcircuit. So for block 1, you have subcircuit 1. For block 2, you have subcircuit 2. Now the subcircuit 1 will have multiple models inside, which are called upon by the lib or the include statement, whatever it is to. And this way, the subcircuit is very different from the model concept. That is the SPICE model concept. So subcircuit is different. So don't think the subcircuit is same as the model. There is similar thing to the model. No, it's completely different. The SPICE models are different. The subcircuit is different, and the purpose with respect to the VLSI design is much more different. So any of this subcircuit will have multiple models of the multiple components. So the subcircuit is a superset of the model, where the model is the subset of any particular subcircuit. So that you have to understand. We are done with this infographic slide. Let's move on to the next slide. Now we come into the detail of the model in entire simulation concept. Previous slide we have talked about subcircuit. Now we are going to explain the model. So this is our circuit or the design block, and inside we will have active elements, passive elements, independent sources, dependent sources. All these things will be there, and they will have the model using the compact model. Now the compact model is the BSIM model or the BSIM category of models, which we have seen in the first episode of the Verilog A, and which is now concised in the Verilog A Marathon. Link is given in description below. In case you are interested, go ahead, watch that particular section using chapters. So once this compact model for 1, 2, 3, 4, all these things are there, right? They go to the SPICE simulation engine, and what is done? Numerical solution is done on the basis of the models of each of these things by matrix method. We have a matrix concept in the mathematics, right? You have learned the matrix and the determinant in the undergraduate level, right? So that matrix I am talking about. So that matrix method is used for several nodes of data, nodes of the circuit that we are simulating using the SPICE. At each circuit node, there will be matrix of the things will be solved, because there are active element, passive elements, independent sources, dependent sources, and many more things which have different kind of electrical characteristics. So, and all they get accumulated in nodes, and where we use the KCL and KVL to solve them, right? But for any instance of time, for any particular instance of time, there will be matrix of the data from different nodes which has to be solved by a numerical solver like bisection, Newton-Raphson. You have learned all these things, right? All those numerical solution has to be done at each of the node, and at the end of the calculation, the final value will be stored for that particular node. Now, once these multiple nodes, say this is a circuit and we have multiple nodes, right? Once the matrix method solves this particular node like this, all the values for a particular instance of time has been calculated. Now the KCL and KVL will be applied as per need basis, and the current voltage characteristics of the entire circuit will be determined for that particular time point. Now we are done explanation of the model, the dot model, and what its significance and how it is related to the numerical solution, numerical calculation, which leads to the use of KCL, KVL and nodal analysis. All these things inside the circuit. This is explained in a detail. Now let me move on to the next slide. We are done here. Model statement and example. Now we will go in the syntax of this particular model. Let us see. The dot model is generally provided by the foundry in the VLSI domain. Generally, foundry does the electrical characterization of all the active, passive, etc. elements that can be integrated into a silicon wafer. That is a monolithic silicon wafer. So that is characterized by the foundry, and dot model hence comes from the foundry. The syntax is dot model, then mname, then type, then pname, pval, pname, pval. So these are the things. And what does this mean? Mname means the model name, right? And next, pname means the parameter name. So parameter 1, 2, 3, 4, like that it goes on inside a model. These parameters actually go and fit into a empirical equation, and thus it gives a value of the output. And that equation has been there using the BC modeling, right? BC modeling is also known as the compact modeling, and BC models are integrated into the SPICE simulator. Only the parameter values we change here, and accordingly we get different shape and size of the MOSFETs. So what happens when the foundry characterizes the model parameters, they use a wide set of LW variation of the MOSFETs. For that, lots of data are collected. From that, the electrical characterization is performed, and from that all these parameters are extracted on an empirical formula using the curve fitting method. So all those parameters come and sit into the dot model statement, which is provided by the foundry, and hence you can understand this is a cumbersome thing. You cannot do it in the design house. It has to be done in the foundry. Next, pval specifies the parameter value. And here you can see we have some infographics of the active, passive elements and etc. that we generally use in a SPICE deck. You can see all these things in a schematic day to day. Now let us see the example of a dot model. So here is the model name, dot model, mod 1. This is the NPN transistor, and we have some parameters BF equal to 50, IS equal to this. The documentation that is provided by the foundry will contain the name of these individual parameters and their significance. Don't worry, they are there. Otherwise, as a design house engineer, right, you may get all these things in the manual of the particular simulator that you are using. In case of additional data, you can ask the application engineer of that particular tool through any portal or ticket, or in case a site visiting AE is there, you can ask him or her about these details, about these parameters, the name of these parameters. He can give you the details in case you are curious to know. So this is the model statement, and we have the NPN. Now let us see what's inside. Inside we have the definition like this. This is another one, dot model G and NMOS. This is the NMOS, and we have level 49. So MOSFETs have come across multiple generations. So all these generations are labeled by the level comment, and this is the 49 level. And here we have the different characterized parameter. These are achieved by the curve fitting method using a characterization tool. That is a software which reads all the electrically, that means physically, electrically characterized data, and all all these parameters are extracted from a wide range of LW variation for the BC model. So these are the compact model or the BC model. These comes from the foundry. So you don't have to write. You will get all these things, right? All these things from the foundry. You have to use it wisely, understanding which model refers to which set of MOSFET. Or in case you are using a FinFET, you will also have the compact model. You have to refer to the right model to get the right result. So there is a BC model for the SY FinFET and there is a BC model for the bulk FinFET. You are using the bulk FinFET in your design. You cannot use the SY model in your SPICE simulation. For that, you have to use only the respective model from the library. So here at this point, you have to be very cautious. The foundry will give you multiple model data, right? But you have to choose which one you have to use. Here, the decision making of the designer who is doing the analog design comes into the picture. Now here we are done. Let's move on to the next slide. Now, here we will go description of the passive elements that we have generally in day-to-day electronics as well as we use them in the SPICE deck. So here there will be simple definitions and some graphics for your understanding. These are resistors, ceramic capacitors, electrolyte capacitors, and inductor coils and transformers. So what are the SPICE nomenclature? All of this? R is for resistance, P is for capacitance, L is for inductance, PC1 linear temperature coefficient, PC2 quadratic temperature coefficient, PCE exponential temperature coefficient, VC1 linear voltage coefficient, VC2 quadratic voltage coefficient, IL1 linear current coefficient, and IL2 quadratic current coefficient. So these things you will find in the SPICE models. Maybe these things you will find in the model or the SPICE text. And these are the components that you use, right? So we are done here. This was a very short and sweet slide to educate you. You can note it down somewhere in your notes what all this means so that you are not get surprised when you see any of this in your design as a SPICE deck. So you are done. Let's move on to the next slide. Model types, active elements. So this is diode, this is BJT, this is MOSFET, this is the IC, that is the integrated circuit, and this is another type of IC which is a regulator IC. So all these are made of semiconductors. And what are the respective SPICE names? So here starts, D is for diode, NPN is for the NPN BJT model, PNP is for the PNP BJT model, NJF is for the N-channel JFET model, PJF is for the P-channel JFET model, NMOS is for the N-channel MOSFET model, PMOS is the P-channel MOSFET model, NMF, N-channel MESFET model, MESFET is different from the MOSFET, PMF is the P-channel MESFET level, P-channel MESFET model, VDMOS is the power MOS model, and AMP is the operational amplifier model. Any of them or all of them or some of them you can come across. Once you get educated, you will be easily identifying these and accordingly you can take your action. We are done here. Let's move on to the next slide. Here we discuss about some more model types. These are OPT is the optimization model. Plot is the plot model for the graph statement. W is the voltage controlled switch. CSW is the current controlled switch. URC is the uniform distributed RC model. LTRA is the lossy transmission line model. U is the lossy transmission line model, that is lumped. W is the lossy transmission line model. SP is the S parameter. In undergraduate level, you have used the S parameter for multiple calculations. Core is the magnetic core model. So these are some extra things that you get in the SPICE. Obviously, these are in the practical world and hence they are ported into the SPICE using all of these notations. So this was a very short and sweet slide about the description of all of this and we are done here. Let's move on to the next slide. Here we talk about the subcircuit command. A subcircuit consists of SPICE design elements that can be defined and referenced in a fashion similar to the device models. This can be written by the VLSI designer. So the SPICE subcircuit can be written by a VLSI designer when that person is designing a block, as we have depicted by the infographics at the very beginning of this particular episode. Subcircuits are the way SPICE implement hierarchical modeling. As we have seen in the infographics that there could be design blocks, inside that there could be sub blocks. Although we have kept a simple infographics in this particular episode, but it could be complex. That means there is a block, then we have a sub block, inside that we have another block, and all of them could be in the SPICE. So first this is designed, then it is used in this, and then this is used in the this. So this kind of design architecture we have explained in the P curve of the VLSI design, and that is you will get in the Verilog episode. Link is given in the description below. However, any subcircuit instance is flattened during the parsing. That means whatever included files are there, they are read from that particular remote location, and that particular code is expanded into the present code so that there is no longer a path and link, etc. This flattening is done during the parsing and just before the simulation. However, that remains internal to the simulator and that doesn't get changed in your input SPICE deck. That is one thing you have to know. The subcircuit is defined and delimited using the dot subcircuit and dot ends card. So the subcircuit and the dot end S, that means these two act as a opening and closing parenthesis like that for containing the block of code that refers to a particular block. So here is some circuit. It's a random picture. Don't try to understand it. I have just kept it for your understanding. So there are resistor, IC, right? Capacitor is there, right? And all these things, right? So any circuit will have multiple such kind of components, right? So each of them may refer to a subcircuit, which will have the nomenclature like this: subcircuit, then subname, then node 1, node 2, node 3, etc. And it ends with the dot ends command and then the subname. So this subname will be here and this will be here too. So this two acts like a opening and closing parenthesis to contain the SPICE code of a particular block. Say this IC is designed, right? The IC name will be here, or the block name will be here, and the block name will be here. In between, the code for this particular block will be written. Now, how the subcircuit is called or instantiated? It is called as X, then the names, Y are the names, and then node 1, node 2, node 3, and then the subname. So this subname is also have to be written here. This way the subcircuit are called. The X instance. Example, first there is a definition block, subcircuit V divide. So this is a voltage divider circuit and we have 1, 2, 3, 3 nodes. R1 is 1 to 10K. R2 is in between 2 and 3, it is 5K, that is 5 kilo ohms, and this is 10 kilo ohms, and this is 5 kilo ohms. Then we have end statement. So this is basically two resistors are in series, and we have a voltage here applied here, and here we get a tap. So this is the output, but we don't have this entire thing. We have just this particular section defined in the subcircuit of a voltage divider. That is the beauty of the subcircuit. You define the thing and later this voltage and etc. will be connected by the designer in the bigger block. So we are done defining the subcircuit. Now, once we have to instantiate, how we'll do that? Like this. So X div1, then we give the first node, second node, and the third node, and we instantiate with the name, that is V divide. So V divide is here. So we give that. So this is the definition and this is the usage or the instantiation. The instance is like that. X will be the first character and all these Y will contain the name that we want to give it. So it could be alphanumerical. So this is an example how a subcircuit is defined and how it is called. We are done here. Let's move on to the next slide. Dot leaf structure. So here we will have an infographics just to understand how the dot leaf thing works in actual VLSI. That means how different things stays in different places, and from there how they are incorporated and how they are included, all these things. This is the background and here is the first part. So this is our netlist, and if you have a close look, we have resistance here and you can see there is a dot lib command here, and we have the lib name, that is the my process dot lib, and then we pick the TT section from this particular lib, and then we have our MOSFET and in-channel MOSFET defined, and then the SPICE deck ends. Now if we try to find out where this particular dot lib is there, how it looks. So if we go and open this particular dot lib by maybe gvim or maybe nedit or any other text viewer, you will see this. So there will be multiple sections inside the .lib file. So the typical example, this is not from any particular cases that I have previously worked. That means it's a demo.lib file and it doesn't belong to any of the real cases, but it's look very similar to the real-time.lib. So here will be .lib, then TT, it starts and closes with NLTT, and here .libff and NlibFF. In between, all the details will be there. The parameter values will be there from the empirical formula, and here is an inline comment, right? Typical process, and this is fast process FF. So these are inline comment. So the .lib will contain multiple sections, TT, FF, SS, all these things from the different process corners. All these things, all these parts will be there. You have to pick the right particular section by using the name of that particular subsection or the .lib, right? The TT is picked up. In case you want to pick the FF will go here, and this particular section will be instantiated in this particular SPICE deck. However, here this particular section is getting instantiated in this. When this netlist is flattened just before the simulation, this particular block of code will be copied into this deck. Now your question is that, okay, I understand this is the .lib, and where all the data is there. That means you said about the vsim data and all the electrically characterized data. So here you can see there is a .include, right? So a .lib can contain a .include. So .include is just to include any kind of file. So here you can see there is a data. In Linux, the file extension does not have a meaning because Linux is going to read the file. It's not like Windows. However, we keep a extension just to differentiate in a human perspective or a human view one file to another. So this file is the dat file, and let's see what's inside it. As we go and open it with any text viewer, it shows like this. So this is the first thing, line, it's a comment start, and here you can see model in channel, and we have all the parameters here. One more thing, not only the SPICE netlist that you are writing will be written in the SPICE syntax. However, any file that is included will have to be in the SPICE syntax. So this means this file also follows the SPICE syntax, and this file which is included or this file which is included will have the included file in the SPICE format. That means how many level of inclusion even you do, each of them have to be in the proper SPICE format. So you can see that this is there. So here we are done explaining how the real-time SPICE.lib will be there. Once you go and simulate inside the VLSI industry, it will have this kind of hierarchy. It could be jumbled upon, or there may be a bit difference. However, this is a common structure that is used in the VLSI industry. So this is a very good slide for you as a learner for the VLSI, that this is why this series is meant for the VLSI, because once you learn these things in the college days, you will not get all these extra or additional information which is applicable and which is very much used in the VLSI industry. However, this is not any proprietary data that is in front of you right now. This is a just handmade example, and this will help you to get educated about how the things are there in the VLSI world. And this is where this particular SPICE series get differentiated with any of the SPICE series that is for your classroom learning. So we're done here. Let's move on to the next slide. Here we will talk about the lib and dellib. So these are very two important commands, and this is very much used in the SPICE in the VLSI industry, and you will see why. So let's begin. We have the .lib command, .lib, then file name or file path, whatever is applicable, then the entry name. This we have seen already. Entry name is the entry name for the section of the lib file to be included. This we have just depicted in the last slide. File name is the name of the file included into the data file. File path, path to a file. Now we go for the details. .lib, then library file definition statement. We have .lib entry name 1. Any valid set of SPICE statement could be here. Then we have endlib, that is the ENDL, and then the entry name 1 as we have seen in the last slide. Then we have entry name 2. Any set of valid SPICE statement, and then we have entry name 2. We have seen this in detail with example in the last slide. So now this is getting more interesting, as this is the example of a real-time usage of .lib in the VLSI. Example you have seen in last slide, and this is a generalization or the syntax you can say. And the dellib statement helps using these multiple libs. You can run, say you are using multiple set of data inside a single SPICE deck. How to do that? So you can change that one particular lib to another particular lib, you use once and then use the del lib command. And generally this is used with in combination with the dot alter, or in case you have some other mechanism in your particular SPICE simulator that will help you to use the lib and the del lib. Del lib, then file name, file path, and the entry name. That means this thing. The entry name used in the library call statement to be deleted. That means we want to delete this lib from consideration. We have to use the del lib, then this particular lib name 1 or the entry name 1. File name is the name of file for a deletion from a data file. File path is the file name of a path if the operating system supports the structure of directories. Okay, so this is the thing. You have a larger SPICE deck, and as you have seen that this library from the processes TTFFSS. So in case your entire SPICE circuit is defined here and somewhere you use the dot alter statement, there you first you simulate with the dot lib all this thing, then we have a dot alter statement, then you change from TT to FF. You change using the del lib statement and it will run once again with the SPICE code, but this time it will discard the first library and pick up the second library. This way you can generate multiple set of data for multiple particular corners as we have seen. And this could be anything, not only corners. In case you have some other variety of the .lib, you can use them. I have given just a particular scenario of usage that you can correlate with the real-time VLSI application. And that's all for this particular slide. Once you get into the VLSI industry, you will use this .lib and del lib statements for the actual VLSI simulation. We are done here. Let's move on to the next slide. Let me summarize what we have learned today. We have learned about the lib and del statement, that is the lib and the del lib statement. We have learned how to use the include statement and seen that include can be used inside the lib, or it can be used independently to include any of the files or any section of code. Next, we have seen the model statement and we have seen the subcircuit, and we have seen the difference of these two. That means the model statement and the subcircuit statement, how these two are different and how they can be included in the VLSI SPICE simulation. That means the real scenario where the model and the subcircuit is there, and the real scenario where the .lib and the include are used in real-time VLSI applications. All the data shown are dummy data. They do not belong to any real data. However, they are very much look-alike in actual scenario of the VLSI, how these things are done in the VLSI design by a analog design engineer. So that's the summary. We are done here. Let's move on. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, common issues in SPICE simulation and how we can troubleshoot. Here we will talk about some pointers that you can follow, remember and note down, so that in upcoming episodes we are going to discuss multiple commands and etc. etc. Starting from this episode, we'll go in deep detail of multiple commands, and associated issues are listed up in a lookup table manner in this particular slide. So you get the details later and you get the initial lookup table, what to do when, in this particular slide. Next, we will talk about dot option general. We will focus on this particular command that is used inside SPICE. Next, we will talk about the dot option for OP, that is operating point and DC. Now, OP is a concept that you have from your textbook. The operating point for BJT, you can remember that we have to know the Q point, right? And the DC means whenever a circuit is turned on, it needs DC, and next it can have AC superimposed on it. However, the base level DC have to be addressed to this particular DC command, and we will go in detail of these things. Next is the dot option for AC and TRAN. So AC is the AC analysis and TRAN is the transient analysis. Transient is with respect to time. So x-axis you have time, y-axis you will have your waveform, and this type of analysis is called transient. And AC, generally there is also x-axis, but however this will have some frequency and this will have your waveform. Okay, so that's the AC. For these things, you have some options, and these are very crucial options for the simulation. And let me speak, many of the advanced VLSI tools, say whether it is in the ASIC design or it may be some in physical design, right? So there multiple tools may use the SPICE simulator inside. Another example is the characterization engine that use the SPICE internally. So that time these options are very crucial. If you do not set them right, you are going to have multiple crashes of SPICE decks, and you will come to know only once you enter the VLSI. Before that, I cannot tell anything about that. There are these options, the dot option general, dot option OP, DC, AC, TRAN, all these things will have a great significance and a great impact. That is the reason we are discussing this. And before that, we are having a mapping table right here so that you can have a clear guidance why you are learning this. Next is the element specific dot option. We will go for element by element here. Next, we will talk about a not set command. There is an operating point, right? There is a similar concept for not set. Not basically is the nodal point. So in a circuit, there will be multiple nodes, right? Nodes where multiple interconnection or junction are there among the different circuit components. So these are nodes, and these node values can be set with an initial guess. That means whenever the numerical engines are used, right, they need an initial guess sometime to start their numerical operation. So for that we need some numerical guess, and that is set by the not set command. Say there is a crucial node, there is a drain of a MOSFET. So there we set some value, and that will take as an initial guess, and then the numerical engine starts from there and do the rest of the calculation. Those are needed, because otherwise the simulation will run infinite, it will crash, something like that. Unusual behavior will come. So that's why we are talking about these things. Next is the .IC, that is the initial guess, and initial guess and the not set, these are two similar commands. However, there are some differences. Once we go in detail, you will find out the differences. So here we will stop in today's episode. In a nutshell, we will be talking about the dot option statement, dot not set statement, and dot IC statement in this episode. So that's the menu for today. Without any further delay, let's begin. Common issues and troubleshooting. Whether you are running a SPICE, directly using a SPICE simulator, or any advanced SPICE that are used in today's VLSI industry, there will be issues definitely once you run. Whether you are doing an analog, means a functional simulation, or you are doing some type of electrical characterization, you will have to face issues. That is the reality. And you have to troubleshoot them also. So here in this slide, we'll talk about them, and you will have a mapping of what to do when here. So let's start. First one, the SPICE is not running. Reason is active SPICE syntax in the first line of your netlist file. So remember, there is a asterisk and there is a comment in the first line of every SPICE file that has to be maintained. If you start writing from the first line, your SPICE, say you are defining a voltage source here, that will not be counted and that can be ignored, and hence the SPICE may not run at all. So you have to be very careful. SPICE run is crashing. You start the SPICE run, after some time you see it has come out, the simulator has crashed. And what is the reason? The reason is the accuracy or the tolerance setting is improper. Now how the accuracy and the tolerance you have to set, we will come to the later dot options and etc. today. So you see that. And in addition to these particular SPICE options, there can be some tool specific option that may vary from one vendor to another vendor Even you have 3 different SPICE simulator from 3 different EDA vendors. They might have additional tolerance or accuracy settings defined by their own. For that, you have to consult their tool manual, not the SPICE language. The SPICE language do have some impact, but on top of that, when the simulator is running, they can have their own option to deal with difficult situations. So those will be there. You have to be aware of them and you have to use them properly. Next is the SPICE run is stuck. So that is the convergence issue. Convergence issue comes from the numerical simulation. That is the, say just for an example, I am saying Newton Raphson or bisection. So they start with some point, they start to progress, and at some point they cannot converge. So that is the convergence issue. Obviously troubleshoot that. For that we have today's episode, the dot option, dot not set, dot IC, all these are there. So we have to tweak judiciously them so that the convergence issue is tackled. So how you will detect what to use? There will be a log file of the SPICE tool. There will be some warning, some messages. You have to scan through it. You have to comprehend where the problem is coming, and then you have to accordingly set the major commands that we are going to discuss today. No waveform or output dB. So there is a probe command we have talked about earlier, and in case you give a improper probe command or no probe command at all, this scenario might happen that there is no waveform output database has been come out, even the simulation has finished without any error or warning. This might happen that you have not given a probe command, or you have given a probe command which is syntactically incorrect, or you have given a to probe some waveform that is not there. There could be human mistake, so you have to be careful. Next, the waveform is distorted. Initial operating points are wrong. In today's episode, we are going to talk about the .IC and the .NOT set, right? Those will help in this particular situation to correct the waveform from the initial distortion. And if there is initial distortion, later on, the behavior of that particular wave as per the functionality of the circuit may get impacted. It will show weird behavior that is not expected from that simulator, but that is not functional incorrectness that might come from the initial points. That is the initial point guess. Runtime is too high. The accuracy is too tight than needed. So accuracy here, first of all, is very much tightened. That means you are running a very high accuracy SPICE simulation. That time, runtime can go too high. There is I said earlier, right? There is matrix calculation that happens inside the SPICE, right? So for that, every node has been taken care, and each node there will be a matrix, data matrix, right? So those have to be solved in the matrix method and all. Now, if you give a too tight high accuracy, these solutions will take time by the mathematical engine inside the SPICE, right? And this is the reason your SPICE run becomes too slow, because you have set the accuracy high, and each point, because it's a dynamic simulation, it's not a static simulation, every time point, every time step, each node, and like this node, everything has to be calculated. And then the time markers moves one time step forward, and again at that point everything is calculated. So if you give a high accuracy, the time for each of these node calculation, right, inside the circuit will go and take much higher time, and as a result the cumulative time will be much higher. As a result, what will happen? The SPICE run will go slow down, and you are thinking what's wrong. So this is the thing, runtime is too high, your accuracy is too tight, you have given a very high accuracy run. You have to reduce some accuracy. Another aspect is that you have chosen a low-end machine. Like in the LSF or UGE, you have chosen a low-end machine where the computational power is less. So you target a high computational power machine through LSF or UGE, right? That can also contribute for this kind of troubleshooting. That is the hardware aspect. However, from the SPICE aspect, the accuracy is too tight, and hence the run is slow than your expectation. So there is no basic guideline that this run is high, this is low. This is as per your expectation. That the SPICE run will take 2 hours to conclude, right? And it is taking 2 days to conclude. So that is too high, and the reason is you have given a very high, that is a very tight accuracy. Next point is the dot measure output is blank. The dot measure command is wrong. So there will be a text file which will contain all the results from the dot measure, right? You see it's blank. So that means you have given the measure command wrong. That means either you have syntactically put it wrong, or you are doing a measure over a waveform, right? You have chosen some points which are maybe outside of this waveform, or somehow the calculation that cannot be done here. So you have chosen this time window, which is wrong. So anything could be there. You have to physically open the waveform and inspect what you are doing wrong by going to the first time point and the next time point in between whatever you are measuring. So this is the part where the measure output is blank. So this is the reason. Command is wrong. That means you have syntactically wrong. That means you have written a totally wrong command, or you might have done something wrong in the physical waveform. So you have given the time on T1, T2, in between you are measuring something, and T1, T2 is in at some point where there is nothing to measure. Okay, so that can happen. Next point is error, the file not found. What is the error? We learned about the .include, .lib, .model, right? Where we are pointing to a path which is there in your hard disk in the work area, right? It may be in a physical machine, or it may be in a remote machine you are accessing through your network, right? So there is some A/B/C/D/ like that path in the Unix, and there is something wrong. Say some folder has been removed here or renamed here, and hence you are not getting the file here. So you have to physically inspect that the file not found. So that means there is a problem happened in the Unix system. You have to go in the Linux terminal or Unix terminal, and you have to go to the path, see what is wrong there. Another thing could be you have used a wrong syntax of the .include, .model or .lib, and hence this error is come. So these are the points which can be the general problems once you are using a SPICE simulation, either for your analog simulation or you are using a SPICE simulator inside through some EDA tool. So there you are facing issues. So any issues more or less will be coming in this point. You have to be very cautious about this, and you have to take action accordingly. And this is not a very straightforward thing. You have to go analyze, check, come back, and then rethink, and then you have to go again and check. So this way you will reach to the conclusion, okay, this is wrong and this I have to change. So we are done with this particular slide. Let's move on to the next slide. Option general. So there will be a few general options for the SPICE simulation. Let us see. This is for the init numerical engines. Okay, so the numerical engines which run in background, right? There is some initialization for them. So we are focusing on those options which are categorized the general option of the dot option. List is the option and it is used as is. Pauses the summary of listing of the input data to be printed. It's a kind of outputting the details of the dot option. ACCT pauses the accounting and runtime statistics to be printed. So you can see at it will give some data related to the accounting or runtime. No at, that means no printing of statistics, no printing of initial transient solution. So nothing will be printed. List causes the summary listing of the input data to be printed. It gives a summary. Node causes the printing of the node table. So there are internal node, important node. I think those will get printed using the node. No mod suppresses the printout of the model parameters. So whatever options I'm talking about is regarding with the NGSPICE, and from one particular SPICE simulator to another particular SPICE simulator, there will be similar options. Okay, similar commands. You have to check the manual for that. But the philosophy remains the same. So you understand the philosophy here for NGSPICE, and then you can map to any particular standard industrial EDA SPICE tool, whether it is a basic SPICE, pure SPICE, or accelerator SPICE, or it's a fast SPICE. So anything, there will be some such set of options. Philosophically, they will be similar to whatever NGSPICE is there, but however, there will be some changes, maybe in the text or something. So you understand the philosophy here, and you can port it to the actual VLSI world. OPTS, that is the ops, causes the option values to be printed. Temperature equal to X resets the operating temperature of the circuit. The default value is 27 degree, that is 300 Kelvin. Now this is a very important, and this is used in almost every SPICE simulation because we have process, temperature, voltage, three kind of variation for the PVT, right? Now this T, even we have the process file from the dot model and etc. as we have discussed in the last episode, right? The dot model, dot lib, how they are accessed. The temperature is finally controlled here to the SPICE simulation. So P process file comes from the SSTT etc, right? I have shown you the model files, how they are included in last episode. The voltage will be given by you as a SPICE voltage commands and options, and the temperature is controlled by this. So this is very important with respect to the VLSI because the PVT, that is the process voltage and temperature, is important in VLSI, and we have an entire episode on these process corners. These are called process corners or PVT corners or PTV corners. There are many names. Why they are important? Please watch the video. We have the link in the description. Now in this slide, we will talk about the option for OP and DC. OP is the operating point, like similar to the Q point of BJT. I am just giving a similarity. It's not the actual thing that we are going to face here. And the DC. The DC means the basic DC operation of a circuit on which we may superimpose AC, pulse train, any kind of transient operation. Let us see the commands. This is the purpose to impact the numerical engines with the initial values. Gmin equal to X resets the minimum conductance, that is default is this value. Conductance we know from our knowledge, right? Next, ITL equal to X resets the iteration limit for the DC. So iteration limit is the iteration limit of the numerical engine for the DC solution. Default is 100. Even you can vary this iteration limit up and down, and accordingly you can help with the non-convergence problem. Now again I mentioned these are respective to the NGSPICE, and you can have similar options in each of the industrial SPICE tool from one vendor to another vendor. ABS tol equal to X resets the absolute current error tolerance for the program. Default is 1 picoampere. So this much relaxation you can give as for the current calculation error. So this is the tolerance. That means you are allowing the simulator to have this much of error, that is acceptable. You need to relax it or tighten it, that is up to you. Once you run the simulation and you get the results, you can tweak with these options as per your need. Pivtol equal to X resets the absolute minimum value for a matrix entry to be accepted as a pivot. Default is this value. So this is a matrix solution. I have told only, right, that for all the nodes we have matrix and we do the solution to it, right? And this option is to impact that particular calculation. REL tol equal to X. So this is another tolerance that resets the relative error tolerance of the program. Default is 0.001, that is 0.1%. So this is a relative error tolerance. So we give a absolute error tolerance, right? And this is a relative error tolerance. So these are kind of way of allowing the simulator to have some inaccuracies so that at the cost of the inaccuracy, you achieve your result within time. Or in case you are stuck for a non-moving point in a SPICE, right? The SPICE SPICE simulation is stuck, right? In that case, you can tweak these options to move out of that situation. Next is the VNTOL equal to X. Resets the absolute voltage error tolerance of the program. Default is 1 microvolt. So again, this is voltage level tolerance that you are giving the relaxation to the simulator, that you can have this much of relaxation while your calculation is there. So plus minus this value is okay for any value calculation that you are doing. So this is how you either tighten the accuracy or you loosen the accuracy. That means you are allowing the simulator to behave as your wish. So folks, these are the few important settings that you use for your simulation, and these are mainly related to the convergence and all, right? So in case you have a convergence issue somewhere, you can look into these options, what is there and how it is impacting. Obviously you have to read and read again the log file to get any relevant messages there, so that by using that you can come to the conclusion where you have to change. And again I am saying these are for NGSPICE. For any other simulator you will have similar options. They may have the same name, they may have some different name. The philosophy will be the same. So we are done with this particular slide. Let's move on to the next slide. Dot option AC and TRAN. So we have some options for the AC analysis and the transient analysis. So let us see them. This is for the numerical engines for the initial, that is the init value. Hence we are giving a label here, and each slide we have such label. So mind the labels. There is a const step equal to X. So X is the value. This is relative step limit applied for code models. Next is the XMU equal to X, sets the damping factor of the trapezoidal integration. These are all related to the numerical calculation, right? Default is 0.5. C8G tol equal to X, resets the charge tolerance of the program. Default value is this. These are kind of options that are more advanced. You may require not in the initial stages of your SPICE simulation or result. You may require some later point where you are doing a functional simulation, and there you may require them. Next is the max evita. Okay, so equal to X sets the maximum number of event iteration per analysis point. It's very simple and straightforward. Next one is the method. So this is a numerical method of integration for SPICE. I have talked about the bisection, Newton-Raphson. Those you learned in the classroom book, that is in undergraduate level. However, dealing with the SPICE, the internal methods, the numerical methods, right? What are they? One example is gear. Another one is the trapezoidal or trap. It is shortened as trap. So you may see gear or trap. There could be some more, right? You have to consult the manual. Default is trapezoidal. Generally, this is the methods that are used. There could be more number of methods. So you have to consult the respective tool manual, the SPICE tool manual, to get what are the available numerical iteration methods. In case one method is stuck, right, you go back to the initial options that few slides back I have talked, or you can come back and you change the entire numerical method and then see what is happening. So it could be better, it could be worse. So you can do those experiments. However, generally any tool company has application engineers. They will guide you whatever is best in which case. So in case you are stuck, you check with them. Either you file a ticket in the support portal. Their application engineers will reply through which you are filing the tickets. Otherwise, if you have a physical application engineer available in your workplace, that person will also guide you. So these are the things that you know when you are working in VLSI. Because for a classroom simulation, easily it goes, right? But for VLSI, you have to meet the target. That means whatever design target is there, you have to meet, and for that whatever you have to do, you have to do. Next is the TR tol, resets the transient error tolerance. Default is 7. The parameter is an estimate to the factor by which SPICE overestimates an actual truncation error. So if there is a truncation error, this will be the parameter to play with. No OPAC. Do not run an operating point analysis prior to an AC analysis. So in some cases it may be needed. Auto stop stops a transient analysis after successfully calculating all functions specified with the dot measure command. So this is another option to play with the transient analysis. We have talked about multiple options. Those are applicable when you are dealing with the AC simulation or a transient simulation. In SPICE, what is the AC simulation? We have a periodic waveform as an input, right? Input vector. And what is transient? Where the output is with time. The time related output. That means in x-axis it will be time and y-axis it will be the waveform. So this way we deal the AC and the transient. AC could be another thing, the circuit which has started oscillating, right? It can output an AC. That is another also option, the AC analysis. We are all done here in this slide. So let's move on to the next slide. Element specific options. So we have some element specific options in SPICE. Let us get familiar with them. Again, these are related to the init numerical engines. When the initialization engine is running, all these options are related to that particular engine. So this is bad MOS3 uses the older version of the MOS3 model with the kappa discontinuity. Since the MOSFET has multiple generations of PC model. So this is one particular option to choose the MOS3 model. DFAD-X resets the value of the MOS drain diffusion area. The default is 0. DFAS-X represents the value of the MOS source diffusion area and default is 0. Next is DEF-L equal to X. Resets the value of the MOS channel length. Default is 100 micrometer. So you can see these three are related to the MOSFETs. DEF-W equal to X. Resets the value of the MOS channel width and default is 100 micrometer. So these all are regarding a MOSFET element and these are not applicable for a BJT. Scale equal to X. Set the element scaling factor for geometric element parameters whose default unit is meters. So this is scaling option. That means what you know about the scaling, right? You know about the lambda, right? In the VLSI technology. Similar things are there. The scaling factor of the MOSFETs. Those are tackled by the scale equal to X. Following instance parameters are scaled. Now resistors and capacitors WL, diodes WL and area, that is the length, width and area. For JFET, MESFET, WL and area, and MOS for MOSFET, WL, AS, AD, PD, PS, SA, SB, SC, SD. So all these things. So these are parameters. Those reside in the BC models, right? And those can be scaled and the scaling control will be done by this. So these are the element specific options. So this way you can tweak them. We are done with this particular slide. So let's move on to the next slide. Not set. Now we are entering into the convergence issues when we deal with what we change. First one we'll talk about the not set and next one we'll talk about the .IC. So they have similarity and difference. So please pay attention. This is for the not set. Again, we are having a label. This is for the not set IC. That is the initial OP, that is the initial operating point guess. The not set line helps the program to find the DC or the initial solution by making an initial guess for a particular node. The restrictions are then released and the iteration continues in true or actual solution. So first, if you tie up a point and from there the simulation starts. So this tie up point is done by the not set. This is for a particular node only. Or multiple nodes you can set using multiple not set command. The final bias point calculated is independent of the not set provided by the guess. That means the Q point, like a BJT, that is calculated and that is separate. But the simulation should start from the for a particular node from that point. Basically, we are talking about, right, it's a transient solution and some point we are starting, right? So that starting point in time t equal to 0, we have some particular node that will contain some particular voltage, right? That is done by the not set. The not set line may be necessary for convergence of bistable or astable circuits. So you know about bistable and astable circuits from your classroom. For those kind of circuitry, the not set will come into the picture and play its role. Here are some examples. Not set, how we use it. V, then node number, then value, then again V, node number, then value. Here it can continue. It can have multiple number of nodes and their values we can set initially in this way. And not set all can be there and all could be have same value. It's a global setting, right? You are using. Then we give an explicit example here. Not set V at 12th node is 4.5 and V4, that is we have a node side. These nodes are defined in the SPICE deck. So there we set 2.23 and not set all equal to 1.5. These examples corresponding to this kind of declaration and this example is for this kind of declaration. So this way we use the not set command to set any particular node to any particular value for the time t equal to 0 or time t equal to t1, whatever is there from where we are starting the simulation. So at the starting point, some node values will be this and then things will move as per the circuit behavior. This is the thing that we do with the not set. We are done here. Let's move on to the next slide. We are talking about the IC, which have a very similar kind of role as the not set, but it has differences. Let us see the differences. And again, I am saying that this is for the not set or IC initial OP guess. That means the initial operating point guess. The first one is the .IC line is for setting transient initial conditions. Next is you should not confuse this line with the not set line. First thing, here is the line of caution. You should not confuse the line with the not set line. And .IC is for the initial transient condition. So transient means in x-axis there will be time and y-axis there will be waveform as per your design output. For this kind of operation, right, the initial guess right, the IC will be come into picture. Not set is for any particular node, right, that you define in SPICE. There you have to set some value. IC is generalized and it's for the transient solution. The not set line is only help the DC convergence and does not affect the final bias solution. This is the striking difference. It has two different approach, whether UIC parameters is clubbed with the TRAN control line or not. So either use the .IC or there is a UIC parameter in the .TRAN command, you can use that. When the UIC parameter is not clubbed with the .TRAN control line, the DC bias solution is computed well before the transient analysis. So DC bias solution, that means the initial calculation of the nodes. There will be lot of nodes and in the circuit, right? For each of them, there should be an initial calculation, and that is well done by the .IC. If you do not use the UIC, UIC will club it with the .TRAN. In this case, the node voltages specified on the .IC lines are forced to the desired initial values during the bias solution. During transient analysis, the constant on the node voltage is removed. This is another thing. These are some constant. The .IC is a constant just for the initial calculation. But those are removed when the transient analysis is started and it is going forward. During the transient analysis, the constant on the node voltage is removed. That means once the DC calculation is done, it's done. And then you move to the transient analysis, and that time these constraints are absent there. The transient will roll in its own fashion. This is preferred method since it allows to compute a consistent DC solution. This method is preferred, right, by the SPICE engineers, or you can say analog engineers, because it gives a consistent DC solution. We are done with this particular slide. Let's move on to the next slide. We are continuing with the .IC. And again, I mentioned that this is for the initial guess or the OP points. UIC parameter in .trans command tells the simulator to use IC statements globally apply on the capacitor, diode, BJT, JFET, MOSFET initial conditions. So this is the specialty of the UIC command used along with the .tran command. We have not talked about the .tran command. Upcoming episodes we will cover that. Here the DC solution is done along with the transient solution and not independently. So the DC solution, when we are using the UIC, it is getting clubbed with the transient solution. And when we are using the IC and we are not using the UIC, that time the initial condition solution is independent of the transient. For manual override, local IC statement can still be present there to take precedence over the global IC values. So in a SPICE deck, right, there could be global IC command and local IC command. Once you code the SPICE in detail, you will come to these things. Here, theoretically explaining this thing is a bit difficult. Let us see some example. Like .IC, V11 equal to 5, V4 equal to -5, V2 equal to 2.2. This way we can use the .IC, or simply we can remove all those things and we only have the .IC. So in this two fashion, you can use the .IC. These are very crucial things of a SPICE. Even if you use an industrial simulator, the .not set and the .IC are very much important, because this will decide how the simulator is kickstarting the simulation. If the kickstart is wrong, then the entire simulation will go wrong. So for that, these are very two crucial points. You have to be very careful about them, and you have to use them cautiously, judiciously, as per the need. Once you consult the log file, you will come to know what wrong has happened, and accordingly what we can change in the .IC or the not set. It is not expected that as a beginner you become proficient in using .IC or .not set, but over time, or in case you have some experienced person in your company, you can take the help of that person, or you can take the help of the application engineer by filing a ticket in the support website, by telling the situation or giving the log file, right? And this way you will have a working experience. So whatever we have talked here is a theoretical experience, and when you work in a company, you will get some working experience which will be additional to all these knowledges, and those are case specific knowledges. With that note, we are done with this particular slide, so let's move on to the next slide. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the alter concept along with the parameter concept, and we will learn how both are used together and how PARAM can impact the alter. With the help of infographics, we will understand the whole scenario. Next, we will talk about the PARAM, that is the parameter, as a global variable. We will talk in two directions. One, how it is impacting the alter, as well as how this global variable is impacting the SPICE as a whole. Next, we will talk about the param with various examples. In these various examples, we will understand how the parameters can be used efficiently to control any part of the SPICE deck. Next, we will talk about the impact areas where the alter can impact in the VLSI SPICE. Next, we will cover the coverage and limitation of the alter state. And at this point, we will conclude our today's episode. Before proceeding any further, I would like to mention one thing. In some of the simulator, it is used as .alter. In NGSPICE, it is used as a alter in the control section. You remember we have a control section at the end of the SPICE deck, which is exclusively for the NGSPICE. So there we use the alter. And in multiple SPICE simulators, the .alter is used as .alter. That is why I am saying interchangeably as .alter and alter, because in NGSPICE you will find it in the control section of the SPICE deck. So the concept or the philosophy of the alter is same. However, syntactically it is used differently in different EDA vendor simulators. So you must be prepared so that whatever you learn here, theoretically that will be same for all the simulator. However, syntactically there will be some change from one EDA vendor to another EDA vendor. So without any further delay, let's begin. This part today which we are discussing is broadly categorized as the simulation control. That means how we control the simulation. Here in this slide, we will talk about the concept. That means the philosophy of alter and the parameter, how they can be used together in VLSI SPICE. Before going any further, I would like to show one thing here. Say you have a SPICE deck here and you have some statement here. For multiple cases, you need to change this statement and rerun the SPICE deck. So that will be very cumbersome. That means every time you have to manually change this statement, then rerun, store all the output results, and then you have to go again, change here and run. And in this process of storing, you have to make sure you keep it in some folder, right? So there you have to do it manually. So this is a very cumbersome process. Now, if there is a mechanism by which you can automatically reset all the changeable values of this particular statement, and automatically different nomenclature will be created for different set of values, right? All those data rather than databases will be created with different nomenclature. That will be a good thing for a VLSI SPICE engineer or VLSI analog design engineer. Now, this feature is alter. Again, I am saying interchangeably this could be a .alter as well as this could be a alter. Now, let us see with the infographics how this is done. Here is your SPICE deck, which you have written in your analog design. Now, simulation will run with the primary setup. That means whatever you have written here, right? All the statements, right? Here you have written, all those will run with the primary setup. Now, when the alter comes into the picture, first change, which you have already included using the alter, what will happen? The simulation will rerun with the altered parameter. Here comes the word parameter, and that's why we are using the .param. However, you will see this alter philosophy is not only limited to the parameter, but it is extended to many other features of SPICE. Again, we have the second set of values with which we want to run, that is with the alter 2. And what will happen? The simulation will rerun with the entire process with the altered parameter. So we have some value here and we have some value here. This is some value here and this is some value here. So these two are different values and the SPICE will run. So this is a very small and simple infographics to understand. However, this change could be numerous. Say 10, 20 changes are there. So in those cases, the entire simulation will be run, and as a result, whatever the output database is coming, right, that database will be renamed accordingly, and then all those databases will be saved. And there is another fact, you don't have to run manually again and again by hand. Rather than you set all these parameters here in the SPICE deck, whatever the list of values will be used in the multiple alter statement, and they will run automatically. And at the end, it will finish and you will have
separate databases for all the altered parameters. Why this is important in VLSI? In VLSI, sometimes we need to change some of the values to see what is the figure of merit is coming out of that particular parameter. Why the figure of merit is important? Because when you are doing an analog design, your design will have some characteristics like frequency, voltage, etc., right? Gain, anything could be there. Now, this figure of merits can be impacted with set of change in the input. Now, this figure of merits can get changed with some change in the input parameters. Now, you have to decide which parameter is impacting in which way, so that when you create a proper documentation on the figure of merit of your analog design, whether it is a block level design or it's an analog IP, that time you have to be cautious that these factors can impact. So as a designer or as a verification engineer, analog verification engineer, this has to be in your mind, so that you have this picture that okay, these points can impact the design output or the design performance. Now here you have the option to tweak the inputs, not the test vectors. First of all, here we are not changing the test vectors. The test vectors, that means whatever input signals are going into the analog design, we are not changing that. We are changing different internal parameters of the circuit design. And that is how we judge that the figure of merit of that particular design, how it is getting impacted. And that's how we list down all the values, and finally we create a documentation of the figure of merit. This is the purpose in VLSI of using the alter philosophy along with the param. And again I am saying the alter philosophy do not only work with the dot param or the parameter, it also works with many other factors which you will learn in this video only. Here we are done with the infographics. Let's move on to the next slide. Param, the global variable. Now let us see the parameter, how we can use as a global variable. You know about the global variable, local variable from the programming language like Perl, Python, Tcl. You already know. We have all these series in our channel. So you know about the global variable concept. Now in SPICE, how this we can introduce? We can introduce this global variable concept with the help of param or parameter. The param is a shorthand of the word parameter. So let's learn about this parameter. First, the syntax is like that: param, then parameter name 1 and its value 1, then parameter name 2, value 2. All these are space separated. So here we have a space, and again we can give a space and we can write here parameter 3 equal to value 3. So this way we can continue and we can write multiple parameters in a single statement. Sometimes in VLSI we do what? We write separate statements, because this parameter could be one category, another set of parameter can come from another category. So we do the separate categorization by separate dot param statement. That is a convention that we can use while we are writing the SPICE deck in VLSI. It sets the global values. That means whatever you set as a parameter, right, that can be used anywhere inside the entire SPICE deck, right? So that's why it is the global value, or it is the global variable similar to the programming language like Perl, Python, etc. Parameterize input element towards model data. So this is the flexibility of the parameter concept or the parameter philosophy, that we can extend it up to different input element, different input source and model data. We can use it in multiple ways. So it's a kind of Swiss Army knife that can be used not only as a global variable but also as to parameterize different input elements of the SPICE deck. Algebraically manipulate output print or plot variables. That is another utility central to circuit optimization and multiple simulation runs. So this parameter, as I said, the parameter has a deep connection with the alter philosophy or the alter statement, and that is used for multiple simulation runs. Let us see some examples here. First, here we write the parameter WP is equal to 50 micro, LP equal to 0.6 micro, LN equal to 0.6 micro, ABC equal to 10. You can see these are in bold. So upcoming lines will have all these parameters and they will be in bold. So watch out for the upcoming lines. Here we have a inverter, right? The instance is x1 and we have here its different values of its parameters. However, we are not using the param here. That means we are not using the values here. However, in next step, we will see. Here we have the dot subcircuit and we have the set of input outputs, or the subcircuit name is here, and we have all the parameters. Now, inside that, when we write a MOSFET, right, we use these global values. You can see WP is coming here. So this value is coming here. L is equal to LP. So LP coming here. And M is equal to APC. So APC 10 value is coming here. Although these are individually defined, so they are not impacted. But however, here, these values are impacting here. Next, we have another MOSFET, that is the N MOSFET. We have W equal to WN. So although we do not have defined WN here, we should have defined the WN equal to something here, and that value would come here. Ln is coming here, and M is equal to, here there is a typo, CBA, it will be something here. We write CBA here, another parameter, and that should come here. So this way, we use the global values in the SPICE deck anywhere. And these values can be used in a multiple ways. And what we are standardizing here, if you look carefully, we are standardizing the MOSFET size and etc., the MOSFET parameters that we are using throughout the entire design. This way, we are making sure that we are using the same size MOSFETs throughout the design. So we can have multiple subcircuit definition inside one particular SPICE deck in VLSI analog design. So there, this way we are standardizing. That means we are defining here and we are using it throughout. Next, we end the subcircuit. So you can see how the parameter can be used as a global variable, which is very similar concept to the global variable from the programming language like Perl, Python, SQL, etc. This way, we can use the param as a global variable. We are done with this slide, and let us move on to the next slide. We have seen one particular use of parameter concept as a global variable in the last slide. We have seen one particular use of parameter as a global variable in the last slide. Now in this slide, we will see some more various kinds of example. So here, we signify various colors here to see various examples. Now let us start. Defining your own functions. Param can be used to define functions. These are inline functions. How? Let us see. So dot param, then we give a function name, then we give argument 1, argument 2, and then we have the parameter expression. So this is a generic way. These are very simple things that we can calculate. Example, we have gain, then we have out, then in, and we have V out by V in. So this is the function that will calculate V out by V in, and this will give a gain. Next, we have print statement. Inside that, we are using this. We are using this particular gain print. We are printing the parameter, right? And we are using the gain, right? And again, we are writing my gain is equal to parameter, then again gain 31. So this way we can use it. Now we define parameter raise equal to 10k. That means 10 kilo ohms. Then we can write parameter t time is equal to 12,000 m, that is millisecond. Then we write parameter v area is 100. Next we write t time 10 is equal to t time by v area. So this way we can go on define parameters and we can use a previously defined parameter like this in the next parameter as an expression, right? Next, we can use it for random control of voltage Gaussian distribution. This is a randomization. So here you can see our voltage, DC voltage is defined, and we are using a predefined function that is T random, and here we are using T time 10. So T time 10, this one is getting used here to generate a random voltage value. Behavioral register. So this register is not a flat register. This has some functionality, and that functionality is defined by the parameter. Now you can see that resistance this between two nodes, and R is defined by this expression race. You can see race is coming from here, and we have some expression 0.033. So you can see in this expression the race is coming from here. Plus we have some fixed numerical values multiplied by res, which is again coming from here, and then VR. So VR2 is coming from a particular node. So this way we can have behavioral register, which is not a simple but some equation based register. These are some wide example of the parameter that can be used in the SPICE deck. We are done here with this particular slide. Let's move on to the next slide. So in this particular slide, we will talk about alter, and we will talk about different areas where the alter can impact. First, the entire simulation runs with the primary or initial setup, and then the alter block causes rerun a simulation several times with different alteration in the wide spectrum of things. Now this wide spectrum of things are listed down. Let's see the list. First is the circuit topology. Next one is the models. Next one is the library components. We know already about the SPICE lib, and they can be changed with the alter philosophy. Next, we have the elements. Circuit elements also can get altered by the alter philosophy. Next, we have parameter values, which already we have came across. Next, we have different options for the settings and etc that we already know from previous episodes, or something which we may come across upcoming episodes. Next, we have source stimulus. Next, we have analysis variables, and we have print or plot commands must be parameterized. That means there should be a parameter included either in the print or the plot command. So all these wide spectrum of things can be impacted. That means can be altered with the alter philosophy. And this is the overall introduction to the alter philosophy along with the parameters. Once you go deep down the analog designs in VLSI, you will come across all of these things one by one and in case by case basis. We are done with this particular slide. Let's move on to the next slide. Here in this slide, we will talk about the coverage and the limitation of the alter philosophy. Now, first, the alter can include. Now we are going in a very explicit manner what the things can be there in the alter. Previous slide, we have talked philosophically or as an overview. Now here we will go in an explicit manner. Element statements except source, .data, .lib, .lib, these two has to be used in coupling or in sequence to activate or deactivate one library, then inclusion of the next library. Next, we have the include. We include some file, .model statements, etc. Next, we have the .ic, .not set statements, which already we have discussed in last episode. Next, we have the .op, the .options. Parameter we have already talked about in this episode. .temperature, that is the temperature of the entire simulation. TF, TRAN, DC, AC, etc. So all these things we can include inside the alter philosophy. That means we can use these along with the alter philosophy, whether it is a .alter command or alter philosophy in the control section of the simulator. Now we will talk about which we cannot include. Here is a fencing. Fencing means you are barred to use them. We cannot use print, plot, grass, any other IO statements. We talked about that we can use parameterized ones, but the simple ones we cannot use. Avoid adding analysis statements under each alter block. Analysis means we do the transient, AC, DC, all this type of analysis. That should be avoided. The analysis will remain same. However, we can include all this type of things inside the alter philosophy. And we cannot include this type of thing until or unless they are parameterized. So here we are done in a very short and sweet manner. So let's move on to the next slide. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the print statement and we will give couple of examples so that you can understand how this is used. Next, we will talk about the probe statement and we will also give some example so that you can understand how this is used. And by covering these two sections, you will be able to differentiate how the print and probe command are different in terms of the output. Next, we will talk about the dot measure statement. We will go in detail and This is the smaller shorthand of dot measure, which is usually written in the SPICE deck to save some characters and for quick and easy writing of the command. Next, we will talk about the significance of dot measure command in VLSI, where in the different areas of the VLSI, this has a impact, where the measure has a impact in the different sectors of VLSI. Next, we will go through the basic example of dot measure command. Next, we will understand the trigger and target philosophy, which is used along with the dot measure through infographics and example. Infographics and example will complete your knowledge. Next, we will talk about different flavors of the dot measure when it is used for find and when. That means when something has occurred. Obviously with example. Without example, it's difficult to understand. Finally, we will talk about the dot measure, how the parameter that we have already learned, that parameter thing, how we can club it with the dot measure to calculate complex equations. In a nutshell, in today's episode, we will talk about the print statement, the probe statement, and different flavors and usage of the dot measure statement. So this is the menu for today. Without any further delay, let's begin. Today's episode is focused on the output control of the SPICE. So this is the philosophy that we are going to cover in the entire episode today. So let us start about the print statement and example. So this is a simple print statement. We have a dot print, then we have a type, and then we have voltages. And where does the output goes? When you give, all the output will go to the terminal where you are running the SPICE, as well as they will be captured in the log file, which is nothing but a text form of whatever comes to this particular terminal as a .log file. Obviously the .log file is a text file, so whatever you give as a print command will go to the terminal, you can see there, as well as in case you are running it through the LSF, you can get it after the run has finished from the .log file. Next, here is the print statement and you can see how it is used. P node. So circuit has nodes, right? All like this nodes. So these nodes will have voltages and in between say there is some component, right? So that element will have the current. For I, it will be the element. For V, it will be the node or parameter. How it will be there? Equation. And this thing we will cover at the last slide, so you have to wait for that. However, all these things, whatever you give in the print will come into the terminal as well as in the log file. The dot print line defines the contents of a tabular listing of the output variable. Generally it comes as the table. When you give all of these things, they will come in a tabular format. The type, here we have talked about the type. The type are like the analysis types like DC, AC, transient, noise, this too, for which the specified output is desired. Generally when we run a SPICE, right, we do any one of this type of analysis. So we also have to provide that analysis type here. That is mandatory. Now let us see some examples that will clear your mind. Print, this is TRAN, that means we are doing a transient analysis. Here we have V4 and V in. So we have voltage and current measurement values. So this will go into the terminal as well as in the log file. Next we have print, then we are doing a DC type of analysis. Then we say V2, VSRC, it's a component, and V between the two nodes. So there are two nodes here. Here, this is 23 number node and this is 17 node. So in between, what is the voltage? We are getting that value in the terminal. Again, we have print and then we have AC type of analysis. And here again, you can see this is VM. Again, this is between two nodes 4 and 2. VR is at particular node 7 and VP is again between two nodes 8 and 3. Now here we have the print, and now this is a good feature of the print that we can also go down the hierarchy in a subcircuit. So subcircuit is defined as x1 dot something will be here. We need all the subcircuit current, so we have to give a asterisk, right? And also there is another way of giving a question mark. So this way we can get all the subcircuit currents. Now, suppose there is a further down deep level of hierarchy. So, x1 dot x2. Obviously, the VLSI designs will have different hierarchy. So, there is a block, inside that there is a sub block, and again inside that sub block there will be another further sub block. So, this way we can go down and then we can get all the currents like this I sub, and I sub is like that x dot a and like that. So, this way you can get the different values of current and voltages, right, down the hierarchy, and this way you can get at the top level, that means where you are doing the analysis, right, and this way you can go deep down inside the hierarchy. We are done here with the print statement. Let's move on to the next slide. Probe statement and example. Let us see how the probe statement functions. Here you can see there is dot probe, then we have a vector, then we have further vectors. Probe is similar to what we measure by the multimeter, connecting it continuously with the breadboard and wires. Otherwise, you can imagine that you are connecting a CRO. So, probe is that kind of operation. So, dot probe, there is another type of way of using it, the analysis type. And then we have the things that we want to print, current, voltage, etc., whatever is there. Use probe significantly decreases the size of simulation output file. When you probe specifically to a set of voltages or currents, right, that will discard unnecessary voltages and currents to be saved in the output database or output raw file. Analysis type is the type of analysis for the plot, like we do the analysis DC, AC, transient, noise, or distortion. So all these types of analysis we do. The analysis type has to be specified along with the probe. You have to remember. Next, OV1, the output variables to be plotted. As I mentioned that these are the output voltages, currents, etc. So these are output variables. These are voltage, current or element template variables from a DC, AC, transient, noise and distortion analysis. Names of the vectors to be saved in the raw file or the DB file. Sometimes it is DB. So DB file or the raw file will contain the output variable in terms of the waveforms. Examples, let us see some examples to better understand the probe command. Probe I V in, then we have input and output. So these are nodes. So we will get the values of these things. This is a simple use. This is another use. Next we have the probe DC, then we have voltage nodes. So this is the most used form, right? We have the analysis type and then we have the nodes or elements. This is a very simple thing to understand and simple command to use. And if you forget to give any probe, right, your output raw file or the output DB file will be empty. That we have already discussed in the troubleshooting episode. So here we are done. Let's move on to the next slide. Dot measure, abbreviated dot MEAS statement. Let us see what's the philosophy and the examples. Dot measure is a post processor. That means once your probe command is done, right, the waveform has come into the DB or the output raw file. The dot measure will operate on it and give you some specific value. The dot measure statement is used to analyze the output data of a transient AC or DC simulation rather than you can say all these types of analysis. These infographics help you to understand. So once your breadboard is ready, there are multiple things in it. You use the multimeter to get a particular value in between 2 points or 2 nodes or a particular pin, right, with respect to the ground. So this is the purpose of the dot measure. Dot measure is a kind of getting a fine-tuned value of what you are looking for. The dot measure command is executed immediately after the simulation has finished. So it operates once the simulation is finished and the entire waveform is saved in the DB. It prints user-defined electrical specification of a circuit. Generally, this is used for the electrical characterization. What we do with the SPICE mostly used in the VLSI electrical characterization. That's why the dot measure is a very important thing. From one simulator to another simulator, this dot measure can have different names. However, the purpose of the target will be the same. 7 fundamental measurements modes. So there are 7 category of things that we can measure. That means we can electrically characterize with the dot measure or the measure command or the measure philosophy, you can say. What are these? Let us see. First one is the rise fall delay. Next one is average, RMS, mean, max. These things I think you are already well aware from the definitions from your textbook. What is the average value? What is the RMS value? All these things you can measure with the dot measure command. Then we can find with respect to time, find when. So find when this is this value. So you will get the time. Next is the equation evaluation. This is another form of thing that we can do with the parameters and all. We will come to know in the last slide. Next we have the derivative evaluation. That is again it comes under the equation and etc. Integral evaluation. And finally the relative error. So all these things we can measure or we can get the values as a electrical characterization from the measure philosophy or the dot measure command, whichever applicable. Any simulator can have this philosophy with a different name. So you must be well ready to accept the philosophy and not just stick to the name. So here we are done talking about the measure philosophy, how it performs, on what it performs. We are done here. Let's move on to the next slide. Dot measure in VLSI. Now this is a kind of philosophical slide rather than having explicit details to know where the dot measure used in VLSI. For all IP related electrical characterization, that means if it is a analog IP, it is a analog digital mixed mode IC, it is a high speed IP like USB, SerDes, all these things. So there the electrical characterization is done by SPICE or SPICE Verilog co-simulation, and there the dot measure philosophy or the measure philosophy is used for this type of characterization. And next is the dot liberty characterization. You already know this is a standard cell characterization. Obviously there will be an engine which does the characterization, but at the unit, that is the cell level or the leaf level, when a electrical value is characterized, that is with the help of the measure philosophy. And sorry about the typo here in between the two characterization words. Okay. Next point is the SPICE dot measure. SPICE is broadly used in analog design and analog electrical characterization. So there you will see the dot measure philosophy. So that means in the three broad areas, this is the analog design, this is the IP design, and this is the standard cell design. So all these areas, you will find the impact of the measure philosophy to measure electrically characterized values. In upcoming slides, you will know the philosophy in minute detail, what are measured, how they are measured, and you will see the graphical example. So done here. Let's move on to the next slide. Dot measure basic example. So here you will see some basic example, fundamental examples that will help you to grasp the meaning. So this is the syntax. We are not going in detail. Here is the basic set of waveforms that we generally find. So this is sine wave, this is square wave, this is triangular wave, this is sawtooth wave. You know all of these waves. And let us see some example. First, dot measure TRAN. So you can see in this x-axis we have time, that is t. And here we have some voltage or current value. So this is a transient analysis. So TRAN, then average value, average of V10 from 10 nanosecond to 55 nanoseconds. So suppose this is V10 and we are trying to get the average value here by the AVG, average mathematical performance. Average, you can see average, mean, max, etc. will be there. And from 10 nanoseconds to 55 nanoseconds. So this is 10 nanosecond and this is 55 nanosecond. So within that we will calculate the average value. So the mathematical form of average calculation will be applied on this particular waveform for this time window. Now we can replicate this if we change V10 to other waveforms. So we can calculate the value for within this particular window for all of them. For that we have to write multiple measure statements. We will change here V10, which say this is V10, V11, V12, V13 like that. Next is the max value, that is max V12. Say this is V12, 1 and 2, in between 1 and 2 node number 1 and 2, from 15 nanosecond to 100 nanosecond. So this is 15 nanosecond and this is say 100 nanosecond. So we will get the maximum value. Generally this is a flat, right? But however, there can be a maximum value somewhere here. We have to detect that. And if we apply rather than a square wave, if we look at a sawtooth wave, right? This is much more applicable because here we are getting a maximum value. Here is the maximum value. So if we try to superimpose this kind of measurements on a sawtooth wave, right, what we will find that within this time window, these are the 3 peaks, 1, 2 and 3, and we will get the maximum value. Say this is the maximum peak. So we will get the maximum value using this particular dot measure command. Next, we have the dot measure TRAN. So you can see I am writing in both ways. The dot MES is the shorthand and the full form the dot measure. TRAN, then Y max, then max value from 2 milliseconds, 3 milliseconds. So again, say this is the waveform, the 2 milliseconds to 3 milliseconds. So we want to find the maximum value of V2. So this is V2. This will operate on this waveform and we will get the maximum value. Then again we have the dot measure TRAN, Y max, max at V2 from 2 milliseconds to 3 milliseconds. So this will give the max at V2. Obviously this will not give the Y value, rather than say if this is the max at this value, right, from within this window, it will give the time value. Here the time axis, it will give the time T of Y max. You can read this as T of Y max. So this will give the time. So the max value within this particular window, right, 2 millisecond to 3 millisecond, we get here, right? This is the max value which we get from here, right? But we want to get the time here. At what time? So this will give the time. Next, we have TRAN, YPP, then PP, and this is peak to peak, right, from this. So peak to peak values we can get like this. So peak to peak value means, say we have a square waveform, right? Peak to peak means this peak to this peak to peak value. These values we can measure in this way. In case of a triangular wave, peak to peak means from here to here. So this way we can get a peak to peak value. These are philosophy, all you have learned in your undergraduate level textbook. Next, we have the RMS value, YRMS. So RMS values you will get of, say, any voltage V1 from 2 to 4 milliseconds. So this is 2 millisecond and this is 4 millisecond at time. So this is time axis, right? And there you want to get the RMS. So you can get all these RMS values 1, 2, 3, 4 by this here. Here, say this is V1. And if you change V1 to 2, 3, this is V2, this is V3, this is V4. And this way, if you change, right, you will get all the RMS values of all these kind of waveforms. So by this. Next, we have the TRAN, then average value, Y average value. And here we give the average. And again, we have from 2 milliseconds to 4 milliseconds. So this way, again, you can get the average value. Say we are taking this time window here, and if you change V1 to other, so this is V1, V2, V3, V4, you will get all the average value of all these separate waveforms. This way you can get the basic measurement values. Now we are done here with this simple set of measurements that you can do with the measure. Let us move on to the next slide. This is an infographic slide. Here we will understand the trigger and target philosophy using multiple waveforms. For your knowledge, let me mark here. The trigger is marked in green and the target is marked in pink in all of the waveforms. Second waveform, third waveform, fourth and fifth waveform. All the waveform we have kept the same convention that we have marked trigger as green and target as pink. Now, this is a waveform where the wave is rising. So we are calculating rise time. So trigger means the measure will trigger here and the target means the measure will finish here. So this will measure the rise time. Philosophically, first you have to understand, then only you can use the dot measure command accordingly, as you are going to see the examples in the upcoming slides. Now, what the fall time, right? The wave is falling down here, right? You can see. So the trigger will start here and the target means the measure will finish here. So in between, it will find the fall time. Obviously, it will be measured in the time axis. Here is also, we will measure it in the time axis. But however, the trigger and target will be on the actual waveform. And in case, see, you are doing this trigger and target, right? And the waveform is flat. What will happen? The measurement value will be corrupted. You have to keep that in mind. We have talked about this in the SPICE troubleshooting episode. Now, there are two waveforms. One is the clock, which is coming from the clock. Another is Q, that is the Q of your flip-flop. The trigger can be at the clock waveform and the target, that means when the measure will finish, on the another waveform, that is Q. And generally this measures the clock to Q delay. This is a very widely used measure, clock to Q delay. Here the time will be measured in the x-axis, starting the trigger at this clock and finishing the measure at this target. And here this clock to Q delay will be measured in the time axis. But here you notice one thing, the trigger lies on a different waveform and the target lies on a different physical waveform. So this is the philosophy of trigger and target. So they can be on the same waveform, they can be on the different waveform. Now here the trigger and target, here you can understand, right? These are on the same waveform. What we are trying to measure here is the on time. That means how much time the waveform is on the on state. So this is typically at the 50% and this is typically at the 50%. Trigger, that means the measure will start here at this point, and the target, that means the measure will finish at this time, and this from the x-axis the time will be calculated. This much time is the on time. Again, to remember, both trigger and target will be according to the waveform. Next, we calculate the time period. From the definition, we know that once a complete cycle is here. So you can see if the complete cycle is here in VLSI, whatever we measure for the time period typically at the 50% of the voltage. Our trigger will start here and the measurement will finish here, and this way once we drop this on the x-axis, the time period, right, this particular time value will be counted as the time period. Through multiple examples, you can understand the trigger and target philosophy lying on different waveforms, maybe lying on the same waveform, but however the waveform should be present there philosophically in proper shape and size to get the values. In case you are getting a wrong value, open the waveform, check whether there is something wrong with the waveform. So that's the philosophy and infographics for trigger and target. Next, we are going to go to the detailed example of this trigger and target. So done here, let's move on to the next slide. So here, let us see some trigger and target examples. Dot measure command measures the different DC voltage, frequency or time between 2 points selected from one or two output vectors. There will be an output vector or output waveform. There we will measure, as we have seen by the infographics in the last slide. Measurements of TRAN analysis start after a delay time TD. Generally, we add a delay time because there will be a startup time of the circuit. Generally, that startup time of the circuit or the turn on time of the circuit we put as T delay. So T delay you can find in the command, and philosophically this is the wake up time of the circuit. So we give that time of delay T delay to get the circuit get on. And after that on time, that means when the circuit is waked up, it performs as per expected. And that's why we keep a provision of TD, that is the T delay, that is the initial delay in the dot measure command. Here is the syntax, we will not go in detail, and the current examples are using the transient solution. So let us have the waveforms again. It will be better to understand through the waveforms. First, you can see that is the trigger and target are present, and you can see both are on V1, right? So that means single waveform. So you can see V1 is here and V1 is here. We are operating on the same waveform, and you can see from rise 1 to rise 2. So this is rise 1 and this is rise 2. Value is 0.5. So this is 1 volt, right? At 0.5 volt, we get the T difference. So T difference will be here in the time axis. Again, this can be for this waveform also, but it is not very much interpretable. That's why I am not giving here. Rather than for a square wave or a pulse wave, this is much more applicable, because in digital electronics or the analog mixed signal electronics, right, this will be more applicable, the square wave or the pulse wave. Now again, you can see here, this is V1, this is V1. So this is rise 1 and this is rise 3. So this is rise 1, then this is rise 2, and this is rise 3. So you have to identify in the physical waveform, right, what you are trying to measure. So this is again value 0.5, value 0.5. So whatever time value is within this time window, this will be measured. You understood the trigger and target philosophy from the infographic slide, and here you can easily apply. Next example. Here you can see the trigger happens at V1 and the target happens at the V1. So these are same. We have rise here and fall here. Earlier both were rise, but here is the difference. This is rise, this is fall. So this is the first rise and this is the first fall. So in between we are measuring the time. So this time we are measuring in the time axis here in this third example. Next, we have again the trigger at V1 and the target at V2. So these are two voltages, and here we call it on the fall 3. Say this is V1 and this is V2, right? What will happen that it will be the fall 3. So this is let me erase it and draw it again. So this is fall 3 and accordingly this will be fall 3, right? We expect some time difference. So let me check, this is fall 3 rather than the previous one, right? So what will happen that some value marker will drop here and some value marker will drop here, and we will measure this time. Although here value I think as 0 has come, it will be some numerical value. It is a typo here, please ignore this. And here you can see trigger and target on the two different waveforms. Now here trigger is on V1, target is on V2, and you can see the value is minus 0.6 and minus 0.8 and cross 1. So this is cross means whenever they cross 1. So that means this will be like this. So at minus this value, minus 0.6, and similar waveform, say this is, these two waveforms we are talking about. This is 0.8. So these two waveform will be considered, and for that first one this is 0.6 and cross at 1. So 0.6 is here, right? Minus 0.6 cross 1. So one marker is dropped here in the time axis, and for target this one, say 0.8 is here, right? Somewhere here, and this is dropped here, and in between there will be a time difference. So that time difference is measured. Cross means once these values are just crossed, that means these values will be explicit. So let me erase it and you will understand better. So this is something 0.8. So this value, whenever this waveform is crossing, just drop a marker at the x-axis. That means the time axis. And here when it is crossing the 0.6, here just drop it. This is the difference that we want to measure. So here are two different, so V1 and V2. So this is V1, this is V2, and this is where we are measuring the time difference. So there will be multiple things that you can measure using this measure philosophy in the different type of VLSI characterization that we have already spoken in few slides back, where we have shown 3 different areas where these are applicable. The last example, trigger at 1 millisecond, target V2. Value is 0, cross 3. Say at 1 millisecond, here we are fixing, and target is V2. Say this is the V2 waveform. Value is 0.8, cross 3. Third time when it is crossing. So that value will be given. This is the final. That means this is a target, and say trigger is done at the 1 millisecond here. So this difference will be given by this. Trigger at 1 millisecond. So this is the trigger happening, and target is V2, and value is this when this crosses. So this cross will be done here, and we drop a time marker here, and this value, this particular time window, we are measuring by this one. So this is the philosophy. We are done with lot of example, infographics, and all these things combined. Now let us move on to the next slide. Dot measure with find and when. Now we are seeking the time when things are happening, right? Until the last slide, mostly we were talking about how much time it is taking, and now we will be focused on when it is happening. That means find when this is happening. So that means we have some voltage thing happening at some point, and we will drop a marker in the x-axis, and we will find when this is happening. The find and when functions allow measuring any dependent or independent time, frequency, or DC parameter when two signals cross each other, or a signal crosses a given value. That means we have two signals which are crossing each other at some point, or one signal that is crossing some particular value. So this is x-axis and this value we are crossing. In this case, we use a find and when. Find and when can be used together or separately as the below combinations. So this is what we give as our looking glass to find when it is happening. This is the syntax here, right? Again, we have a large syntax here. We have further large syntax here, and we have another syntax here. But don't worry, we will not go deep in the syntax. The syntax is there. We will understand it through examples. So let us move on to the next slide. So here we will understand the find and when through examples. That is better way to understand. Here again we will need the waveform, so we keep them. Example, start here. Dot measure TRAN fifth when this voltage value is equal to 2.5 at rise 5. So this is V oscillating output, right? And it is 2.5, right, at the rise 5. So 1, 2, 3, 4, 5. So it will go beyond our waveform, right? So we consider this is rise 5. So this is rise 5, right? So it will be 2.5. So 2.5 means this. And when means at what time point? So we are getting the absolute x-axis time point. that is t equal to t1 when we have this rise spike. Dot measure time of the fifth rise of the node oscillating out at 2.5 volt report as the fifth listing. So that is the fifth rise time. First rise, second rise, third rise. First rise, second rise, third rise. So this way the rise and falls are measured. This is the first fall, second fall, third fall. First fall, second fall, third fall. So this way first, second, third are measured. Next, we have the dot measure TRAN, then find, then we have V out. This is another waveform when V in is equal to 40. So this is V out and this is V in. Here we want to find V out, that means here when V in is equal to 40. The measure V out when the V in is equal to 40 m towards the variable result. So this is 40, right? What will be the value of V m? This value will be stored. This is time wise and this is value wise. That means at 40 m, so this is at 40 m, this is x axis, 40 m is here, x axis, and at y axis, whatever we are getting in the V out, this is a V out, this is V out and this is V in. So V in we are taking the x axis, the value, and we are getting the y value at another waveform. Next, measure TRAN P value when V2 equal to V1. Okay, if these two waveforms are bit shifted, right, then if this peak is just below this, right, there will be a value of time, right, when this will be done, 10. And it could be that rise equal to last. So last rise is this one. So here, suppose we drop a marker and at this value and this value are same. We want to know this time value here. This time value goes here. Measure TRAN Y eval, find V2 at the last fall. So this is V2, this is the last fall when V1 is equal to 0.4. So this is V1 and also here this is 0.4 and it is minus, and we drop a marker here and we find the value here. That means we get the Y value. Earlier we are getting the T value. T value means X value. Y value means we are getting the voltage wave. Next, again we get a similar Y values. Find V2 when V1 equal to V3 at fall 2. At fall 2, this is the second fall when V1 equal to V2 at some voltage V1 equal to V2 at that particular time. V1 equal to V3. This is V3. So V1 equal to V3. These two values are same at fall 2. Find V2. This value will be find out. This is V1, this is V3 and this is V. That's all. Next we have Y value, find V2 at 2 milliseconds. So this is a very simple thing. This is V2, find V2 at 2 milliseconds. So this is 2 milliseconds, say this is 2 milliseconds. Go and find the Y value. This is the Y value. So this is the find and when philosophy. Find can be used independently, when can be used independently. So this is a independent use of when, this is the independent use of find, and this is the dependent use of find when. So all are shown to you. Here we are done with the waveform, philosophy, everything. Now let us move on to the next slide. Now here we have the dot measure with the PARAM equation. Use this statement to evaluate an equation that can be function of results of previous dot measure statements. Sometimes we have to calculate some value on the go using dot measure. And there we have to use the parameter that we have already learned in the SPICE in previous episodes. And we have to form an equation. And from that equation, we evaluate some value on the go. The equation must not be a function of node voltages or branch current. So this must be remembered. Dot measure, then measure type, then parameter name, then measure equation. This is the generic form. And this is the syntax. And this is another syntax. So here are multiple set of syntax could be there. This is with find and this is just a simple thing. This is find at. Now let us see some example. You understand anything with example. So I'll focus on the example rather than in the syntax. So here dot measure is a transient type. We find t meet and we have parameter. Here we have t from t2. So we have two time point. We have this and we divide by 2. We have t from and t2 and we have these two value and mathematically we are getting the by 2 value t1 plus t2 by 2. So this is done by the parameter. Yes, with some previous measure command we have measured this t1 and t2 separately and then we calculate t1 plus t2 by. Next we have the parameter, then f value equal to 5. This is a simple thing and this will be used in further calculation. Then we have the dot measure TRAN y at parameter f val, right? This is constant plus 7. So this way we can use a parameter inside a measure. Then we have parameter v out, then diff is 50 micro. Now we are going to use this. Let us see how. We have dot measure TRAN p diff trigger at 1 millisecond, target at v2. We have already come across this type of trigger target already, value at cross 3. So what we get from this one, t diff, and here we have v out diff. Now let us check. With this measure TRAN command, we give a check, right? Then we give param. We have a ternary expression here. This is a ternary operator, right? We know all this from our long back C language. So from there we decide a value to this by comparing this value and this value. That means this is what we have hard coded, and whatever we are getting t diff from this measure, we are comparing them with a ternary operator, and finally we are storing the result here. So this is a part of characterization things that you have to do in VLSI, and that's why I am going through thorough example. Next we have measure, and then we have TRAN, that is a transient, and v test find is a find one. Then we have this value at this one. So this value will be find, some waveform is there, and find at 2.3 millisecond. Okay, this is the x value. This value will be find. We are done here with thorough example how the parameter can be used inside and along with side by side the measure commands along with all other trig tag things. So there could be a complex mix and match of all the measure commands that I have shown you in this entire video through thorough example. They can be used in the electrical characterization done in VLSI in any of the sectors of whether it is could be a IP characterization, it could be a mixed signal characterization, it could be standard cell characterization, anything or any other type of electrical characterization that you can find in any up kind of new design. So that is we have learned in today's episode. We're done here. Let's move on to the next slide. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about simple DC and AC sources. Sometimes we use the DC and AC sources combined together in SPICE decks. So we will give you that details. And this is different from AC analysis or transient analysis or DC analysis. These are sources, that means power sources. Next, we will go towards the exponential and sawtooth sources. Now let us have some visualizations. This is sine wave, generally known as the alternating voltage or current. This is square wave. Sometimes it is called pulse sources. This is triangle, and this is sawtooth. So these are the basic things that generally we come across. We will learn how to construct this type of sources through the SPICE language in today's episode. Next, we will cover the pulse sources. Pulse sources means this one. Next, we will cover the piecewise linear, which is different from anything that you can see here. It has a different form. So we will go in detail later. Next, we will cover the sinusoidal source, that is this one, the sine source. And that's how we will conclude today's episode. So this is the menu for today. Without any further delay, let's begin. Before going any further, I'd like to emphasize that in today's episode, we are going to discuss about the independent power sources. So power sources means this could be voltage sources or this could be current sources. However, these are independent sources. That means they are independent on their own and they do not depend on any other sources or any other factors. So let's move on to the next slide. Simple DC and AC sources. Here we will talk about the basic DC sources coupled with AC sources. Those are practical to see in every electronic circuit. Here is a visual. So you can see that in the y-axis it will be current or voltage like this, and in the x-axis it will be time, that is t. The DC source here you can see we marked with the red called direct, and that will stay horizontal with time. That means there is no change in the voltage level with respect to time, hence it is called the DC. Now here you can see this is a pulsating sources. This is another kind of sources. Generally these are kind of, you see where you find AC ripples like in the rectifier circuits. The green one is the alternating current. Alternating means this is the x-axis and this is plus y-axis and this is minus y-axis, right? This alternating means it is going towards the positive axis, then at some time point it is going towards the negative y-axis, then again it is changing towards the positive y-axis. That means it is alternating its polarity. And this is the variable source. That means this source do not have a pattern, and with time it can have any shape and figure. However, in this particular slide, we will talk about the simple DC sources as well as DC sources coupled with AC source. So let us begin. Voltage. So this is the syntax here. Vxxs, where this will be V1, V2. This X here, they could be alphanumeric. This is first node, this is second node. DC value, in case they have a function here, it will go here. In case it will have AC coupled with it, so there will be AC magnitude and AC phase. Okay, so you know about the phase and the magnitude from your textbook. So those you can write here. So this is the syntax. Next, the current will be like this. I, then YY. So these will be alphanumeric. I will be the first one. Should be there, and there could be alphanumeric after I. Plus node, minus node, and the DC value of the current will be here. Here could be a function. And here, if there is a AC coupled with the DC sources, that has to be mentioned. So here the magnitude will go, here the phase will go. Now let us see some examples. Here the DC source, this is a voltage source V1, it is tied between 1 and 0, and here the DC value is 5 volts. So this is a pure DC source, and we do not have any AC components along with it or AC superimposed on the DC, so it is not there. Again, it can be written as V1, then 1, 0. Those are nodes in between which it is connected. Those are nodes in between which it is connected, and the simple the value, the 5 volt. Next, we have I1. This is a current which is connected in between 1 and 0 node, and it has DC value of 5 milliampere. Let us see some AC sources. Here you can see V1, then 1, 0, okay, and it has AC, that is 10 volt is the amplitude, and phase is 90. And here we have another example. Here is a AC source, right, V2, which is connected between 1 and 0. The DC offset or the DC value, the basic DC value on which the AC is superimposed is 1.5, and the AC voltage is 10 volt and the phase is 90. So this way we can define simple DC and AC sources for your SPICE tech, where you have to power up the circuit that is under concern with any DC voltage or current. So we have gone through the syntax and the example, as well as we have some visuals here. We are done here. Let's move on to the next slide. Here we will talk about the exponential or sawtooth voltage. This is the sawtooth you came across in the first slide. Now once we expand this in terms to do the mathematics, the shape is looking like this. So here we are expanding this part, or you can say this part. This is much more elaborated part. So this will look like this. So first, this is the voltage or the current axis, and this is the time axis. So here you can see this much is TD rise, that means delay before the rise time. Now this is T rise, from here to here this is T rise. You can see the arrow in between where this is rising, right? Sawtooth has a rising time, so we have a rising time. Here we have kept everything similar, rise fall, but in actual case it could be different. Just for understanding we have kept this. Now this point is V2. If we drop a perpendicular on the voltage axis, the maximum one, and the minimum one from which starting is V1. So here this is V1 and this is V2. This level is V2 and this level is V1. Now this maximum point is achieved at TD fall, and from this point we can calculate the T fall. So this is the T fall where we calculate the fall time. This is very easy to understand. I have kept a very symmetric structure here for understanding. However, in actual practice, this could be symmetric, could not be symmetric. There should be alignment as per the need, right? So the rise time and fall time generally, and in picture we can see this is falling very sharp, but however there will be some time, some fraction of time for this fall, right? And the rise, there will be a time, and this could define the exponential also, and we will use here the function, you will see. So the voltage will be like this. So V then XXX, these will be alphanumeric, okay? Node 1, node 2, in between which it is connected, that is the plus node and the minus node. And EXP is the exponential function, V1 and V2. So this is V1, V1 comes here and V2 goes here. So these two levels. Now TD rise, here you can see TD rise here, then T rise, this one, T rise here, right? Then TD fall, let me clean it up. Then TD fall goes here and this T fall goes here. That means once we give all the details, this exponential function will construct the sawtooth wave. And based on the values, it can look exponential, it could look sawtooth, and that's how it is expected. Here the default values are the TD rise value, that means this has the default value 0. T rise, that means this has the default value T step. T step is the time step of the simulation, the transient simulation, because in this axis we have time and this axis we have voltage or current. That will be T step. And TD fall, so this one TD fall will be TD rise plus T step, and T fall, that is this one, will have the default value T step. So in case you are not specifying, you are giving just V1 and V2, right, to this function. Rest of the things will take the default values like this. Let us see an example. Here you can see VIN, it is connected between node 1 and node 0, and exponential. 4 is this voltage, V1, 1 is this, right, this one. Now TD rise here is 2 nanosecond, T rise is 30 nanosecond, TD fall is 60 nanosecond, and T fall is 40 nanosecond. So here you can see all these things here in this particular figure, and that is how you can construct a particular exponential sawtooth wave here through this syntax. We are done here. Let's move on to the next slide. Here in this slide, we will talk about the pulse source. Generally, this is viewed as maybe a square wave or a rectangular wave, but this is generally a pulse source once pulse is coming from a source. So here we have kept the square, right? And to understand it better, we have zoomed like the previous one, and we have multiple factors here defined in this particular figure. So let us see the equation here. Here is the syntax, right? So V, then this could be alphanumeric, and this is node 1, node 2. And once we zoom right, so this factor from, if it is starting like this, right, at this point, so this will be this, and this rise time will be this, then the stable period is this, then fall time is this, and this goes on. So this is a pulse source. So pulse we are calculating, right? So plus n minus n are the two nodes in between the voltage which it is connecting. So pulse is here and V1 is here. You can see this level, that is voltage. So here you can see this one from the base, this voltage is V1, and V2 is the maximum. That means this one is the V2, this maximum one. Here you can see this is V2. So we get V1 from the picture, it is V1, and this is V2, and then we have TD. TD is here. You can see TD is here. Then T rise. T rise is here. You can see the rise time. This is the time for the wave to get rise. Then T fall is here. T fall is this fall, right? So this time is this much time is needed for the fall. So this is T fall. And then the pulse width. So width is here. You can see in between these dotted lines. This is the pulse width. So that is what we have already drawn here. And then we give the period. So you can easily visualize these things. You can see here we have period, and this goes here. So period is from here to here. Okay? This is the period. Now let us see an example. Before that, we can see the default values. So if nothing is specified, T rise will be T step. Again, I am saying this is a transient simulation, so there will be a simulation step. If not specified, this T rise, T fall, etc., etc. T rise will be T step. T fall will be T step. T width, this width will be T stop, right? And period will be again T stop. So you have to specify. Now let us see an example. Here is the example. You can see this is V in, which is connected between 3 and 0. It is a pulse source, and -1 is this one is -1 volt, and this one goes to this V2, and then we have TD as 2 nanosecond, T rise as 2 nanosecond, T fall as 2 nanosecond, width as 60 nanosecond, and period as 90 nanosecond. And from this particular figure, you can see which one is what. So this way we can construct a pulse source. And we also shown the default value. So we are done here. Let's move on to the next slide. Here we will talk about the piecewise linear, and this do not have a pattern. However, this can have a repetitive pattern. That means the pattern that is not fixed like any other waveforms you have seen. So let us see how the PWL looks. So it will look like this. In y-axis there will be current or voltage. Then here time 1, voltage 1. This axis is time. So the first one coordinate is T1 V1. Second coordinate of the voltage after some time is T2 V2. Then T3 V3. So here you can see T2 T3 are same, right? Then again T4 V4. Okay. E5 V5. E6 V6. So at every coordinate the values are changing, and some may change, some may not change. So here something did not change, here something did not change, right? That is the voltage level. Now how to describe such wave? And let me say, after this point this particular pattern will keep on repeating. So here it will repeat itself, this particular pattern. It don't have a regular pattern like already we have seen, but it has a pattern, and that kind of pattern will repeat after some time. So the waveform will go on repeating itself. How to write that? So here is a voltage example or voltage syntax. So here it will be alphanumeric. This is a plus node, minus node, and then we write PWL. Then we give T1 V1, then T2 V2, then T3 V3, and then we go again up to Tn Vn. And R is equal to repeat. That means after some time we need repeat, we have to mention R. Td is the T delay. Here it starts with a delay, right? So that Td will go here. Simple. Now let us see an example. Here you can see V in is connected between the node V gate and ground, that is 0. Here PWL, then it is 0 at time 0, it is 0 volt, 5 nanosecond, this is 0 volt, 10 nanosecond, this is 5 volt. So this way we are defining the coordinates through which the wave is getting created. And this way we reach up to 30 nanosecond where the voltage again goes 0. After that we mention repeat, that is R. That means after this particular point, this particular kind of pattern will keep on repeating. And here T delay, that means this one from where it is starting, T delay will be 60 nanosecond. So this way we can define the piecewise linear source. Again with this one you can create different kind of waveforms as you need. In the SPICE deck it could be voltage, it could be current. We have shown voltage here. However, the current will be similar. Instead of V, this will be I. That's all. We are done here. Let's move on to the next slide. Sinusoidal source. So by the name we know already from our textbook, that is it is a sine wave. And how we draw in on axis here like this. I have kept this free so that you can understand. Now let's see the syntax here. For voltage we are defining the syntax, right? Here this will be V followed by a alphanumeric thing. Then plus node and minus node. Then we have sine function here. Then V offset. Offset means this is the offset voltage. This is from the 0. We have offset. That means it is shifted. It is not on the 0. So offset and amplitude. Amplitude means what you understand by this. So this is the amplitude, right? In graph. So this is the amplitude. The amplitude. Then we have frequency, TD, then damping, then phase delay. So let us see the example. So here V in is connected between 3 and 0, sine, then V offset is 0 and VA is 1, frequency is 100 megahertz and 100 megahertz, and TD, that is T delay. So if it is starting after some delay point, right, small delay, so TD will be this, and damping is this. And we don't have mentioned the phase delay here. Here the phase delay defaulted to 0 or 0 degrees. So that's why it is not there. So this way we can write a sine wave, whether it is a current or voltage. It will follow this syntax. For current, instead of V, it will be I. That's all. We are done here for the sinusoidal sources. Now let's move on to the next slide. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the polynomial source of one dimension. Next, we will talk about polynomial source of two dimension. Obviously, we will give examples so that you can understand and correlate the syntax with the example. Next, we will talk about the voltage controlled voltage source with an example. Next, we will talk about voltage controlled current source with example. Going further, we will talk about current controlled current source with example and current controlled voltage source with example. And that's the menu for today. Without any further delay, let's begin. before going any further, I would like to emphasize a point that in today's episode, we are going to discuss about the dependent power source. That means the power source which we are using to empower our circuit is dependent on some sort of other sources, functions, etc., etc. And that we will go and explore today. So let's move on. First is the polynomial 1D source. That is the one-dimensional. So here you can see that couple of friends are standing together, and we will see similar thing as for the coefficients. Here it is the syntax, it is E, the first letter, and there will be alphanumeric that you can specify, and then there will be plus node, minus node, then degree of variables, then the plus node, minus node, and then there will be polynomial coefficients. So what does this syntax mean and corresponds to? The independent voltage source is here V, which is connected in between plus n and minus n, and the equation of the one-dimensional polynomial source is, you can see y equal to p0, then a, p1 into a square, and that's how it goes on up to pn a to the power n. So this is the polynomial equation, and this voltage will be put as a, and these coefficients are this. This is why you can see plus n minus n is here, and all these coefficients are put after that. For the polynomial equation this, we will have the SPICE equivalent this. Now let me explain and map how this is going on. So E1 is the syntax from here, which is connected in between plus n and minus n. So the two positive and negative node in between the control source is connected is 5 and 0, and we have a polynomial of degree 1. So here it is the degree. Here you can see degree or number of variables. And then we have plus n minus n. Here you can see this voltage is connected in between 3 and 2. So 3 and 2 comes here. And you can see here the coefficient P0 is 1 and coefficient P1 is this. So here two coefficients are mentioned. So this way one-dimensional polynomial equation is formed here through the SPICE syntax. This is a bit difficult or complex as compared to the independent sources. You have to put your mind calm and quiet manner, and then you have to think and correlate. So this is something which is much more complex in nature than any other sources, independent sources you have seen before in last episode. We are done here with the polynomial 1D source, that is one dimensional. Now we'll move on to the next slide. Here we will talk about the polynomial source that is two-dimensional. So here you can see there are two rows of coefficients, that is two-dimensional, and this is just a kind of graphics I kept here. Here the syntax is E, then this X will be alphanumeric, positive node and negative node in between the source is connected to empower, and then we will have the degree of variables, and then we have node 1, node 2, then we have n1 plus and n1 minus and n2 plus and n2 minus. Because this is 2D, there will be two sources and there will be couple of coefficients that defines the equation. Now let us proceed to understand it more. So here the independent voltage source are, this is V1 which is connected in between node 1 and node 2, you can see, and V2 which is connected in between the node 2 plus and node 2 minus. And here it is node 1 plus and node 1 minus. So these are the two voltage sources. These are the independent sources which are controlling this dependent source, right? For two-dimensional polynomial, the equation is, it's a bit complex than before. P0 has nothing here. Then P1 into A, P2 into B, P3 into A square, P4 into AB, P5 into B square, P6 into A cube, P7 into A square B, P8 into AB square, P9 into P cube. So, and this goes on. And for this particular polynomial V10, 3.3 into V32 and 4 into V square. Now this is A and this is B, and you can see here this resembles to this and this resembles to this, and we do not have any other coefficient. So these rest of the things are not here, so we will not think about them and not talk about them. However, you can see this is 0, this is 0, this is 0 and this is 0. So these are absent completely. This happens only these coefficients are 0, P2, P0, P2, P3, P4. Now let us see the SPICE equivalent. Here the SPICE syntax is E1, which is connected between 1 and 0. These two is a poly of order 2, and here we degree or number of variables. Then we have 3, 2, which is these two nodes. These two nodes are these two nodes, and 7, 6 are these two nodes. here. And then you can see P0 is 0. This is 3 because here it is 3. And here this is P, right? And B square. And this is P5. So P5 here goes 4. And in between we have 1, 2, 3 zeros. 3 zeros are here. So this way the polynomial is constructed with the SPICE syntax. The independent sources A here is V32 as we have seen, right? And B is V76. And here A and B are also in the equation. So you have to correlate in a very calm and quiet manner. And this is very different from the previous episode sources where we talked about the independent sources. And here dependent sources are much more complex in nature in mathematical form. The polynomial coefficient, as I explained, P0 is 0, P1 is 3, then we have 3 zeros and P5 is 4. I have already explained this. So we are done here talking about a two-dimensional polynomial source. Now let us move on. Voltage controlled voltage source. So here goes our syntax. So this is E and it would be alphanumeric, node 1 and node 2 in between which it is connected. We give a type, then we have again the independent sources is here in between these two nodes, then gain, max value, mean value, these are upper and lower caps of the voltage. Let us see through examples. The type can be, this type can be VCVS, op-amp, transformer, PWL, poly. Max and mean are the two upper and lower capping limit of the output voltage. The output voltage, the capping limit is here. Behavioral voltage source syntax is E, then XXX, then we have plus N and minus N, right? These two nodes, then volume, then equation. Then again we have the two nodes in between the voltage is connected, then max value, mean value. Example, VCO. We have EVCO which is connected in between two nodes and the equation is like this. We have the equation. Ideal op-amp syntax is here E, then we have alphanumeric presence here with the 3 x's and then we have two nodes op-amp, then plus and minus nodes. So example is op-amp, then we are connected between 2 and 3. Op-amp is mentioned here. It is again two nodes are there. Max is 5, mean is minus 5. So max and mean we are saying the capping limit. Next we have the transformer. Transformer is something, there we have two coils, right? And in between we have something for the separation. So this induces this getting induced by this. So here we have the format. We have two nodes, then transformer, then plus minus nodes. Here key is the mutual inductance. Example is E trans, then out 0, then we have transformer, then in 0 and the mutual inductance is 10. This way we write the voltage controlled voltage source. That means the source which is controlling is a voltage and that the source which is getting controlled is also a voltage. We have given multiple examples and these are complex sources. Obviously you have to put your mind in a calm state to understand the syntax and correlate, right? Not like the previous independent sources which we have talked in last episode. So we are done here. Let's move on to the next slide. Now we talked about voltage controlled current source. These are current source and these are controlled by voltage. The syntax will be like this. Here we have G, then alphanumeric presence here, then two nodes, then type, then again we have two nodes where the independent source is there, then we have the transconductance and max and mean value. Now let us go in detail. The type can be VCCS, VCC cap and VCR, PWL, poly, PPWL, bidirectional switch of PMOS and NPWL, bidirectional switch of NMOS. So here we have a word PWL and you will see in the example how this PWL is signified through the code. Max and mean are the upper and lower capping limit of the output voltage. That means this one, right? Resistor switch, let us see an example here. A voltage controlled resistor represent a basic switch characteristics. How? Here G switch is connected between 2, 0 and this is type VCR, voltage controlled resistor, and PWL. Now that is connected 1 and 0 and here the PWL is controlled within the limit 0 volt and 10 mA, 1 volt and 1 mA. Beyond the voltage capping levels, the resistance values are 10 meg and 1 milliohms respectively. In between, it varies linearly. We have the upper limit and lower limit and we have a voltage controlled resistor. MOSFET switch, now we will go in these switches, right? Here, GNMOS is connected between D and S, VCR, this is VCR, NPWL, right? Where this, next we have these two, these are again G and S. Now MOSFET level is 1, and then we have 0.4 volt 1.5E, 1 volt 10 meg, 2 volt 50K, 3 volt 4K, 5 volt 2K. Now let us see. Here a MOSFET switch is modeled by N piecewise linear resistance switch. Voltage controlled capacitor. Here we have G cap, which is connected between out and 0. Type is capacitor, right? You can see the capacitor, and this is controlled in a PWL manner. And this is connected again. These two are the independent connection, right? The nodes PTRL and 0. Then we have 2 volt 1P and 2.5 volt 5P. Beyond the voltage capping levels, capacitance values are capped at 1 picofarad. This is capacitance value picofarad, and 5 picofarad. This is 5 picofarad respectively. In between it varies linearly. So this is quite complex. Here the examples that you see, that these are very complex sources. These are not very simple and straightforward. So it will take time for you to understand these sources, and if required, you have to write the equation by understanding these examples. That's why I have given a couple of examples for you to understand. Now we are done here. Let's move on to the next slide. Current controlled current source. So here the ultimate source is a current source, and it is controlled by current, which are the independent sources. Now the syntax is F, then we have alphanumeric, 2 nodes in between which it's connected, type, then we have gain, max and mean value. Type can be CCCS, then PW and poly. Max and mean are the lower and upper capping limit of the output voltage. That means the final voltage. Example, we have this equation, right? I F1, this is 5 into IV sense, represented by SPICE. So here you can see F, then we have 1, which is connected between 13 and 5 node, and this is controlled by V sense. And max and mean are plus 3 and minus 3. These are, so remaining is gain, and gain is 5 here. So you can see this 5 comes as a gain at this point. Next equation is I, then F2, then 1E minus 3, then we have this IVCC, and it is SPICE syntax is F2, then it is connected between these two, and this is the polynomial equation. So we have poly, right, and then we have VCC 1A and 1.3 M, 1 million, 1.3. So this way you can define the things. We are done with the examples of current controlled current source here, and these are again quite complex things. You have to put your mind in a calm state and then understand and then write the syntaxes. Done here. Let's move on to the next slide. Now we will be talking about the current controlled voltage source. That means the final one is the voltage source, and it is getting controlled by the current. So here is the syntax. Each, then we have the alphanumeric presence, then we have 2 nodes, type, and then we node 1, and then we have transconductance, max value, mean value. We already know these types. Type can be CCVS, PWL, poly. Max and mean are the upper and lower limit of the output voltage. That means the final voltage. These are the capping limits. Example, here we have a equation Hx 1000 into V current, represented by a SPICE syntax, this one. Hx here, and then these 2 nodes are here. V current is there, which is this, and max and mean value, that is the capping value, and finally we leave the value 1000, which is coming here. We are done here. Let's move on to the next slide. Let us summarize what we have learned today. We have learned about the polynomial source 1D and 2D. We have talked about voltage controlled voltage source with examples. Next we have talked about voltage controlled current source with example. Next we have talked about current controlled current source with example. And finally we have talked about current controlled voltage source with example. So these are the things we have covered in today's episode, and we are done here with the summary slide. Let's move on to the next slide. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the significance of .op in SPICE simulation. Next, we will talk about the significance of .dc in SPICE simulation. Going further, we will talk about the syntax and example of .dc. Next, we will talk about the significance of AC analysis in SPICE simulation. Going further, we will talk about the syntax and example of the AC analysis, that is the .ac statement. Next, we will talk about the significance of the transient analysis, which is short formed as TRAN. Going further, we will talk about the syntax and examples of .TRAN. Finally, we will summarize our today's discussion. So that's the menu for today. Without any further delay, let's begin. Before beginning anything, I would like to mention that this episode and the next episode, we will be talking about the common genre of topics that are called the simulation control. That means how we control the different kind of simulation through different set of analysis. So let's move on to the next starting slide. .op significance. Here we will talk about the significance of the .op. So here goes our .op and it is written as .op only. It calculates the operating point of MOSFETs. Generally, we have a CMOS structure and we know that MOSFETs have some operating points and those are calculated by .op. The inclusion of this line in an input SPICE file directs the SPICE simulator to determine the DC operating point, also known as the Q point or quiescent point of the circuit with inductor shorted and capacitor opened. That means it's purely in a DC format. So all the nodes and the corresponding DC points are analyzed through this one single command. It's a very much kind of short instruction, but it operates on the entire circuit. That means the entire circuit, the whole set of nodes. And inductor shorted and capacitor open means this is in a DC. Several steps are executed to get exact operating point and are documented in the simulation log. That means whenever you have a terminal, right, the terminal will give you the chronological output of the SPICE simulation. There you will have also there will be a log file generated that will also have. So all the operating points will be given. Nowadays modern simulator has an option either to display all these things or suppress those things. So you must check also the modern simulators that whether this dumping option is opened or the dumping option is closed. This dumping option may vary from one simulator to another simulator, and here we are not talking about them, just touch basing the concept. It reports, that means the .op reports the following things. First, the node voltages, as I have mentioned, there will be a huge number of nodes in the circuit and the source currents. So there will be detailed calculation and the initial guess, that is the Q point, that means this Q point are calculated for all the node voltage and the source currents. Next, power dissipation at the operating point. So we have an operating point, right? It's a DC point and we calculate the power dissipation happening everywhere in the circuit in all the nodes. Semiconductor device currents, conductance, capacitance, that means all the circuit element factors that are going to take part in the upcoming analysis, which might be a DC, which might be a AC, or which might be a transient or any other kind of analysis. So those are pre-calculated using the .op statement. The reporting may vary from simulator to simulator. This is, I also mentioned few lines back that the log may have well documented details of these operating points, or it may have that those are suppressed. So that depends from one simulator to another simulator. You should check the options to suppress or explicitly print all those options. Or even we are printing, there could be a shorthand print or it may be a explicit print. So that vary from one simulator to another simulator to shrink the size of the log file to save the disk space. So you must also take care of these options when you are using a proprietary simulator in the VLSI. We are done here with this particular slide by depicting all the significance that is associated with the .op, that is this much small command in this particular slide. Let's move on to the next slide. Here in this slide, we will talk about the significance of the .dc statement. The operating point or Q point, the quiescent point analysis is very crucial before performing full DC or AC analysis. That means we are calculating an operating region where the initial voltages of every node of the circuit or device under test, that is, it could be a MOSFET or it could be a CMOS, whether all those things are at the correct voltages points. So the operating point analysis, that's why it is very crucial. In DC analysis, capacitors and inductors are considered to be open and short respectively, as also we have talked in last slide that inductors will be considered open to DC because inductance is associated with AC only and capacitance is also associated with AC only. If it is DC, the capacitor will be open and the inductors will be short. So that is the assumption that we take when we do the DC analysis. .IC and .NOT set are very important at this stage. So have talked about the .IC and .NOT set already in the previous episodes. If you have not seen, I request you to see because these are explained in detail. DC analysis and operating point analysis statements are .DC, this sweeps for power supply, temperature, parameter, transfer curves, so all these things. And the .OP is for operating points to be calculated at specific time. So that means the DC is for sweeping the DC, but before anything we do, we must get the quiescent point or the Q point or the operating point through the .OP. That is the philosophy before beginning any simulation in the SPICE. So that must be there before we begin any kind of analysis. We are done here talking about the significance of the .DC through this slide. Let's move on to the next slide. Here in this particular slide, we will be going in detail of the syntax and example of .DC. So here is the syntax .DC, then we have the source name, then we have start value of the voltage, stop value of the voltage and incremental value of the voltage. And in case we have some other source that can be also there, so source 2, start, stop and incremental value. Start means it will start at some value, stop means it will stop at that value, increment means there will be steps by which the voltage will get incremented. The .DC line defines the DC transfer characteristics curve of source and sweep limits. The source name is an independent voltage or current source of a resistor or the circuit temperature. Here could be a temperature also. In using the DC, we can also sweep the temperature of the circuit. V start, V stop and VINCR are the starting, final and incrementing values. So these three are explained here. Let us see some examples of the .DC. Here is the first one, DC, then Vin is the source name, then 0.25, 0.5 and 0.25. This way we say that Vin sweeps from 0.25 volt to 5 volt at the step of 0.25 volt. So you can correlate, this is start, this is stop and this is increment. This way you can correlate. Here example is DC, VDS, then 0, then 10, then 0.5. Then we have source 2 that is VGS, then 0, 5 and 1. So how we interpret it? We interpret this syntax as this sweeps VDS from 0 to 10 volt, that means from here to here with the step of 0.5, that means this is the step, and VGS sweep is from 0 to 5 volt at the step of 1 volt. That means for each of this sweep, right, there will be multiple VGS sweep. That's how it happens. Next, we have another example which is for the temperature. Now we write DC, then we write temp, and then we have the -55 to 125 and the step is 10. So how we interpret this? We interpret that the temperature is swept from -55 degree centigrade to 125 degree centigrade at the step of 10 degree centigrade. So in the first two example, we have seen single DC sweep, multiple DC sweep, and in the third we see the temperature sweep. Next, we have another example. It has much more bigger thing. So here the DC is there, the source is VCE and it starts from 0 goes to 10 at the step of 0.25. So how we interpret? Here the VC is swept from 0 to 10 volt at the step of 0.25. Now here again we have another source. This is a current source and it starts with 0 goes to 10 at the step of 1 micro. So how we interpret? Sweep the value of IB starting from 0 to 10 micro at the step of 1 micro. And you know the unit of current is ampere, so we add an ampere, that means microampere. So you have learned how to do the current sweep along with a voltage sweep here in this particular statement. Finally, we have another kind of DC sweep, that is the DC. Then we have RL load. It is a resistance. We have 1K, 2K as the starting and finishing line, and we have steps as 100. So how we interpret? Resistance sweep is done from 1K to 2K at the step of 100 ohm per step. So here you can see multiple kinds of example of the DC syntax. You can see the single DC voltage sweep, multiple DC voltage sweep. You can see the temperature sweep, the resistance sweep, and the voltage and current sweep. So you have seen 5 different kind of example that you can do the permutation and combination. This way you can apply the syntax as per your requirement. We are done talking about the syntax and thorough example. Let's move on to the next slide. Here in this slide, we will talk about the AC analysis. Mainly we focus on the significance. After doing the OP analysis, which we have talked in the first slide, right? SPICE simulator can conduct AC analysis of the nonlinear device such as MOSFET at the DC operating point. So once the Q point is done, then we can go ahead for the AC analysis. The .AC statement can do the sweep of multiple things containing frequency, element value, temperature, model parameter value, random sweeps such as Monte Carlo, optimization, and AC design analysis. So all this sort of thing are taken care by the .AC statement. Don't worry, we'll have examples for multiple things. There you will be understanding this significance. If this line is included in the input file, the simulator performs the AC analysis of the circuit over the specified frequency range. So we will do the frequency variation, right? And then variation, we can do the AC analysis of the circuit. Note that in order for this analysis to be meaningful, at least one independent source must have been specified with an AC value. So we need one particular independent source which has AC value. Typically, it does not much sense to specify more than one AC source. Obviously, in AC, either we will vary the voltage or the frequency, right? So there it doesn't make sense to have multiple AC in the same circuit. Generally, there will be a DC and a superimposed AC. If you do, the result will be superposition of all sources and difficult to interpret. So that means if we take more than one AC source in the circuit and try to analyze, the final outcome will have the cumulative effect of all the AC sources, and that will be very difficult to interpret, analyze, or debug. So that is the significance of the AC, and the things that we can get from the AC analysis are discussed here. Let's move on to the next slide to see some examples. Here in this slide, we will go through the syntax of the .AC and some examples to understand the usage. This is generally a sine wave format, just for your understanding that how the AC you expect, right? This is the most common waveform of the AC. However, AC could be something which has a periodic manner, not limited to the sine wave only. So here goes our syntax. Here we have the first syntax, the AC, then we have the det, that is decade, then ND, then F start, then F stop, then we have another kind of sweep attached to it. The variable, then start, stop, and increment values. We have 3 forms. The second form is the change here is the OCT, that is the oct. And we have the linear. We have 3 different forms. And the different things in this 3 syntaxes means decade means decade-wise variation in the log scale. ND is the number of points per decade. Here you can see number of points per decade. Then we have oct is octave-wise variation. And NO is the number of points per octave. Lin is the linear variation. NP is the number of points. So here NP. We have F start is the starting frequency. F stop is the final frequency. So here is the F stop. So these are the things that you must know about the AC syntax. And here is the first part we have talked about. We will see examples for the sweep part also going further. So without any further delay, let's start the examples. First, we have a AC, then we have a decade-wise variation. Here we have 10 number of points per decade. Starting frequency is 1 and ending frequency is 10K. Next, we have AC and we have decade. Number of points will be 10. Starting frequency 1K and ending frequency 100 meg. Obviously, we are considering the default units of the frequency. Now we have the AC, then linear, then there will be 100 points. Starting is 1 and ending is 100 Hz for the frequency. Finally, we have the example containing the sweep. So first part is AC, then decade, then 10 points per decade. Starting is 1, final frequency is 10K. Then we have a sweep of C load with linear. Here the starting is 20. It will stop at 1 PF and the steps will be. So it seems that there is some typo here. Okay. However, you can understand that how the things will go on for the sweep. So you are done with the all flavors of examples of the .AC. So let's move on to the next slide. Here in this slide, we will be talking about the significance of the transient analysis. Here are some transient waveforms that you can correlate with your general knowledge: sine, square, triangle, and sawtooth. This TRAN compute circuit solution as a function over time, that means the time range. Use of UIC. UIC is a command that is use initial conditions used along with the transients to calculate the Q points for the transient. We ensure to solve the quiescent points, that is the Q point, before beginning the transient analysis. That means this Q point analysis is coupled with the transient analysis and it is different from the default Q point analysis. Transient temperature sweep can be also taken care by this TRAN. Transient Monte Carlo analysis, that is the random sweep, also can be taken care by transient analysis. We can do the transient parameter sweep also. We can do the transient optimization through the TRAN command. Taking .op results as the initial value for the transient analysis. That means the transient analysis can run also with the .op, which calculates the initial Q points or quiescent points and start the transient analysis based off it. Also, alternatively, we can use the UIC or OP. So either you use the .op or you use the UIC, either one of them. So here goes the philosophy of the transient analysis by using the .TRAN statement. Now let us move on to the next slide. Here in this slide, we will talk about the syntax and example of transient analysis. .TRAN, T-step, T-stop, T-start, T-max and UIC. So this gives the transient syntax. T-step is the printing or plotting increment for line printer output. That means it gives the step by which the simulation jumps from one point to another point. T-stop is the finishing line for the time-wise simulation. T-start is the beginning line or the starting line, that is the initial time. If T-start is omitted, it is assumed to be 0. That means the starting line starts from 0. If we do not give the T-start, if it is not stated, means we are missing it. That means the time will begin from 0 value. The transient analysis always begins at the time 0 if this T-start is omitted. Otherwise, if the interval, that is 0 to T-start, the circuit is analyzed to reach a steady value, but no outputs are stored. That means once we specify time 0 to time T-start, calculation will happen. However, the data will not be stored for either for the waveform database or for the log or the text output. Nothing will be stored. All will be calculated and data will be stored from T-start. The interval, that is T-start and T-stop, the circuit is analyzed and the output are well stored for analysis. That means you do a text analysis or the waveform analysis, all the data will be stored. Tmax is the maximum step size default equal to T-step or T-stop minus T-start by 50. So T-max gives the maximum step size. So the step size should not go beyond this value. Otherwise, this will be taken as the maximum step size. So T-stop minus T-start by 50, whichever is smaller. Tmax is useful when one wishes to guarantee a computational interval that is smaller than the printer statement. That means T-step. Here we are done talking about the syntax of the .TRAN and the philosophy of various factors associated with it. Let's move on to the next slide. .TRAN examples. So here is a sawtooth and here is a square, just again for your visual experience. Now let us start the examples. We have .TRAN, then we have 1 nanosecond, then we have 100 nanosecond. What does this signify? This signifies the transient analysis is made and printed for every 1 nanosecond for 100 nanosecond. Here we have omitted the start time. So the start time will be from 0 and the step is here 1 nanosecond. Then we have the TRAN, then we have 1 nanosecond, then 1000 nanosecond and we have 500 nanosecond. Here we have specified the step. Then again we have TRAN, then 10 nanosecond and 1 microsecond. Again, here we are omitting the step. Next is .TRAN, 10 nanosecond, 1 microsecond. We have these two intervals. we have these two values. First one is the step and second one is the finishing line. And with this, we use a sweep for C load. Point of interest is 3 and 3 point of interest are given here. 1 picofarad, 5 picofarad, 10 picofarad. So let us see this by words, what I have just mentioned, right? So this means the calculation is made every 10 nanosecond for 1 microsecond at 3 C load values. Py is the point of interest and 3 values are given here. So here we have seen the transient analysis various examples to understand the philosophy that we have discussed in the previous slide. We are done discussing about the TRAN, that is the transient examples. Let's move on to the next slide. Summary. Let us summarize whatever we have discussed throughout our entire discussion. So we have discussed the simulation controls using the .op and .bc analysis, the .ac analysis and .tran analysis. So all this sort of analysis we have discussed in today's episode. We are done here. Let's move on to the next slide. Hey guys, welcome back. In today's episode, we are going to discuss the below topics. First, we will talk about the noise analysis, which is very closely resembled to the AC analysis. Next, we will dive into the distortion analysis. Again, you will find some similarity here with the AC. And finally, we will conclude today's episode as well as the SPICE series with the sensitivity analysis. That's the menu for today. Without any further delay, let's begin. In last episode, we have started the simulation control. And this episode, we will conclude with 3 different statements as we have discussed in the menu page. So without any further delay, let's begin. The first topic is the noise analysis, which is the .noise keyword. And let us see some details about. Noise analysis is run hand in hand with an AC analysis. It calculates the input and output noise of a circuit. The output noise at a specified output node is the RMS sum of the noise generated by active and passive elements present in the circuits. That is the summary of the noise analysis, the theory behind the noise analysis. And now let us look into the command details. So this is the command. Now let me highlight. So this is .noise is first. Then we have a V, then output node and a reference node. And we have SRC and then we have 3 types of analysis, which is very similar to the AC analysis, the decade, linear and octave. And we have number of points, then F start, that is the starting frequency, and F stop, that is the final frequency. And we have points per summary. That is another additional point that you have not seen in the AC. Here you will see it when we are going through the example in the next slide. Output node is the node at which the total output noise is desired. So this one we are talking about. If ref is specified, then the noise voltage, that is V output node minus V ref, this value is calculated. So this is the voltage between the output node and the reference voltage that we have given. By default, the ref is assumed to be ground, basically the ground of a circuit. And also we can specify some reference voltage here also, or the reference node rather. SRC is the name of the independent source to which the input noise is referred. So it is the source of the noise. PTS, F start and F stop are the AC type parameters that we have already seen, and these specify the frequency range over which the plots are desired. So this is the starting to the ending frequency, and these are the number of points that we want in our graph or in the data, whatever is applicable. PTS per summary is an optional integer if it is specified the noise contribution to each noise generator is produced every PTS per summary frequency points. PTS per summary is an optional integer if it is specified the noise contributions of each noise generator is produced every PTS per summary frequency points. So that is the detail of the command of the .noise. And now let us move on to the next slide to see some example. So the first example here is this one. So here we have noise, then we have V5, then V in, then decade, and 10 is the number of points, then starting frequency and ending frequency. So this is the first type, and you can see it's very similar to the AC, right? And here you can see these two voltages, right? V5 and V in. So these are two things that you can relate with the noise command. Now let us see the next one where we also have the last parameter which we do not see here. So here again it is the noise command. Then we have B53 instead of B5. Then we have B1. Then we have oct, that is octave type of analysis. Then we have number of points is 8, starting frequency, ending frequency, and it is the summary points that we have already discussed in last slide. So these are two typical example of the noise analysis. And here we are done with the noise analysis. So let's move on to the next slide. The distortion analysis, the disto. So here it is explicitly said that this is used with the hand in hand in the AC analysis. The .disto line does a small signal distortion analysis of the circuit. The SPICE reports the distortion measures at specified passive load component. Load components generally are the C, L, etc. right? Or the R. Okay. So these are load components and these are passive in nature. Now the format is .disto. Then we again have the digate, then ND, F start, F stop, and F2 over F1. We will see it later. Up to this you can see this is resembling with the AC analysis format. We also have the octave and we have the linear. Again here these three are number of points and these are very common. That is the starting frequency and the ending frequency. And we will see what is this later on. Let us see some example. Here the distortion and we have decay type of analysis. Number of points is 10. Starting frequency is 1 kilohertz and the ending frequency is 100 megahertz. So this next example is we have disto and then we have decay type of analysis, again 10 points and 1 kilohertz to 100 megahertz, and we have F2 over F is means this part as the value of 0.9. So these are two type of examples. Now here it could be octave, it could be linear, and the number of points can vary, starting frequency can vary, and F2 over F1 also can vary. So we are done with this slide. So let's move on to the next slide. We continue with the distortion analysis details. Now here is the syntax. Without optional parameter F2 over F1, the distortion does a harmonic analysis. So this is a type of analysis that is performed without the F2 over F1, which is a harmonic analysis. In such scenario, analysis distortion in the circuit using only a single input frequency F1, which is swept as specified by arguments of the disto command exactly as the AC command. So here we have the very similarity with the .AC analysis. If the optional F2 over F1 parameter is specified, it should be a real number between and not equal to 0.0 and 1.0. So basically this is a range of this parameter. In this case, the disto does a spectral analysis. That means without the F2 over F1, it does harmonic analysis, and with the F2 over F1 parameter within this range, that is the expected range, it does the spectral analysis. So these two type of analysis we can perform with and without the F2 over F1 parameter. NGSPICE supports distortion analysis only for diodes, BJT, JFET, MOSFETs, and we have the corresponding levels here. MESFET. So NGSPICE has this capability, but it can perform the distortion analysis over a limited number of elements, and these elements are listed here. So we are done talking about the distortion analysis. Now let's move on to the next slide. Here we talk about the sensitivity analysis. Sensitivity analysis is a model that determines how target variables are affected based on changes for a given variable. So this is how we analyze the sensitivity. These are typically what if then scenarios. So in SPICE, if we have to do the what if then analysis, we take the help of the sensitivity analysis. It is the way to predict the outcome of a distortion given a certain range of variables. It is a way to predict the outcome of a decision given a certain range of variables. So with respect to certain range of variables, we conclude something. Is sense, then outward, and then we have the sense, then outward, then AC, then we have decay, then ND, then F start, then F stop. And again we have two other formats, that is for octave and linear. We have that, and you can see rest of the things are very similar. That is we have F start, F stop, right? And we have number of points here, and we have type of analysis, decay, octave or linear, right? And this is the outward. The sensitivity of outware to all non-zero device parameters is calculated when the sense analysis is specified. Generally, we have a lot of device parameters when we have a model for a device, right? Based on them, we can do the sensitivity analysis. Outware is a circuit variable, that is node voltage, voltage source, branch current, etc. The first form calculates the sensitivity of DC operating point value of outware. We are talking about this. The second form calculates the sensitivity of the AC values of the outward. So this is for DC, this one, and rest of the things are for AC. We have done talking on the sense. Now let us see some example of the sensitivity analysis. Here goes our example. First one, sense, then V1, out. So this is a kind of DC, right? As we have spoken already. And then we have the sense, then V out, then AC, then we have decade type of analysis, number of points 10, starting frequency is 100, and the final frequency is 100K. So this way, we have the sensitivity analysis in DC format, that is the DC sensitivity as well as the AC sensitivity analysis. That is sense I VT test. Again, this is for the current analysis and this is for DC. We have reached to the end of this episode. And thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in comments in the comment section down below. And bye for today.